In this exploration, we delve into how reality transforms when the familiar laws of the macroscopic world dissolve into the quiet, fluid logic of the quantum realm. At the smallest scales imaginable, the world begins to behave in ways that feel unfamiliar. Objects lose their sharp edges, certainty softens. Events no longer follow a single predictable path. Light arrives as both ripple and packet. Particles exist more as tendencies than as things. What once seemed solid becomes strangely fluid, suspended between possibilities. As you settle into this moment, let the world outside grow quieter. There is no rush to understand, no pressure to solve. We are simply here to observe the gentle loosening of the rules we thought were absolute. Imagine, if you will, the room around you. To your eyes and your touch, everything has a place. The chair beneath you, the floor under your feet, the very air you breathe, all seem to follow a reliable, sturdy logic. If you drop a pen, it falls straight down. If you close a door, it remains closed. This is the world of the definite, the world of the sharp edge. But as we begin to look closer, past the surface of things and into the deep fabric of matter, those sharp edges begin to blur. It is as if the universe, when viewed through a powerful enough lens, decides that being one thing at a time is simply too restrictive. On a microscopic level, space is generous with its options. Quantum physics did not begin as an attempt to be strange. It emerged because careful measurements refused to agree with familiar rules. Heat behaved oddly. Light arrived in unexpected ways. Matter itself seemed unsure of where it was or how fast it moved. What followed was not a rejection of reality, but a deeper look at it, guided by patience, precision, and a willingness to let go of certainty. Over time, this quiet framework revealed a universe built not from definite outcomes but from probabilities. A place where events are shaped by chance within firm boundaries, where observation matters, and where the act of looking is itself a form of interaction. The quantum world does not hide behind mystery for its own sake. It simply follows rules that feel unfamiliar to human intuition. Tonight's journey moves gently through that world, not to solve it and not to force it into neat explanations, but to rest with its strangeness, to explore how reality behaves when certainty loosens, and to notice what it feels like to let questions remain open. Settle in, let the sharp edges soften, and allow the strange quiet logic of the quantum world to unfold slowly. It is a story about limits, uncertainty, and the surprisingly gentle rules that govern the smallest pieces of reality. A story that does not demand answers, only attention for as long as it feels comfortable. What if the universe at its deepest level is not built from solid things at all, but from possibilities quietly waiting to become real? Think of a grain of sand. To your finger, it is a tiny, hard speck, but to a physicist, that speck is a buzzing hive of activity, a collection of atoms that are themselves mostly empty space. And yet, within that emptiness, there is a structure so precise that it holds the world together. However, that structure is not made of tiny bricks. It is made of fields, ripples, and waves of probability. When we talk about the softening of certainty, we are talking about the moment we realize that the solid world is actually a beautiful, shimmering projection of something much more fluid underneath. In our daily lives, we are used to the idea of either or. A light is either on or it is off. You are either in one room or you are in another. But the quantum world suggests a both and approach. Before a particle is measured, before it is forced to account for itself by bumping into something else, it exists in a state of superposition. It carries within it all the places it could be, all the speeds it could be moving, and all the paths it could take. It is a state of pure potential. It is only when the microscopic world meets the macroscopic world, the world of detectors, eyes, and touch, that the universe narrows its gaze and chooses a single outcome. This narrowing is not a loss. It is simply how the universe transitions from the infinite possibilities of the small to the singular reality of the large. Consider the way a melody exists. Before the notes are played, the music is a set of possibilities on a page or a thought in a mind. When the first note is struck, it is definite, but the melody itself requires the notes to hang together in time, overlapping in memory and expectation. The quantum world is like music. It is a series of relationships rather than a collection of static objects. When we invite ourselves into this microscopic view, we are leaving behind the rigid architecture of the clockwork universe. We are stepping into a world that is more like a vast, quiet ocean where every ripple affects every other ripple, and where the depth is far greater than the surface suggests. As you listen, you might feel the urge to visualize these particles as tiny marbles, but try instead to think of them as notes of a flute echoing in a large hall. The sound is in one place, yet it fills the room. It has a center, yet its edges are soft. This is the true nature of the quantum world. It is a place of resonance rather than collision. The uncertainty we find there is not a mistake or a flaw in our vision. It is what gives the universe its flexibility. Without this built-in blur, without this softening of edges, atoms would be too brittle to exist. The very stability of the matter that makes up your body depends on the fact that electrons refuse to be pinned down to a single, sharp point. As the world outside grows quieter and thoughts begin to soften at the edges, we can begin to appreciate the elegance of this design. The universe does not hurry to make up its mind. It allows itself to linger in the maybe, moving through a space of likelihoods with a grace that classical physics could never describe. This is an invitation to let go of the need for a single, hard truth. In the quantum realm, truth is a distribution, a beautiful curve of probability that tells us where things are likely to be, while always leaving room for the unexpected. It is a world that breathes. Tonight, we do not seek to master these equations. We strive to feel the shift in perspective they offer. We are moving away from the heavy, mechanical world of the 19th century and into a landscape that is light, airy, and interconnected. In this first chapter of our exploration, we simply acknowledge that the world is deeper than it looks. We accept that beneath the solid surface of our lives, there is a quiet, rhythmic pulse of possibility. The certainty we once leaned on is softening, but in its place, we find something far more interesting, a universe that is alive with potential, waiting in the dark for the next interaction to bring it into focus. For now, there is nothing to do but drift. The science is steady, the mysteries are vast, and the microscopic world is waiting to show us its true soft face. In this stage of our journey, we step back into a time when the world felt entirely understood, only to witness the exact moment the foundations began to tremble. Before we can appreciate the strange fluidity of the quantum world, we must understand the rigid perfection of the world that came before it. At the end of the 19th century, physics felt settled in a way that is difficult to recapture now. The universe appeared orderly and cooperative, governed by laws that were not only reliable, but reassuringly smooth. Motion followed clean paths. Heat flowed in predictable directions. Light behaved as a wave, spreading gently through space according to equations that had been tested again and again. There was a sense quietly shared among many physicists that the great structure of reality had already been uncovered, and that what remained were refinements rather than revelations. This confidence did not arise from complacency. It grew out of extraordinary success. Classical physics explained the workings of engines and bridges, the behavior of gases, the ticking of clocks, and the motion of planets with remarkable precision. It gave the impression that nature, once mysterious, had finally agreed to be understood. With enough patience and careful calculation, it seemed that almost any physical question could be answered. Almost. The first sign of trouble did not arrive with a dramatic contradiction or an exotic experiment. It appeared in a place so familiar that it barely raised suspicion at all. It began with warmth. Imagine a simple piece of iron placed in a forge. As the metal absorbs heat, it begins to glow. At first it is a dull, deep red. As the temperature rises, it brightens into orange, then a brilliant yellow, and finally a searing white. This glow is not decorative, it is radiation emitted as the vibrating atoms within the object release energy into their surroundings. This relationship between temperature and emitted light was easy to observe and seemed, on the surface, easy to explain. This behavior was known as blackbody radiation, a term for an idealized object that absorbs and emits all frequencies of light perfectly. Classical physics approached this problem with total confidence. Heat was energy, and energy was something the equations handled well. The leading theory of the time suggested that as temperature increased, more energy should be available to radiate away at every possible frequency. The mathematics suggested that hotter objects would emit more light at higher frequencies, shifting steadily toward shorter wavelengths as the temperature rose. When the calculations were fully performed, however, the results became impossible to ignore. According to the established equations, the energy emitted at very high frequencies should increase without limit. As the wavelengths grew shorter and shorter, entering the ultraviolet range, the predicted radiation surged upward, racing toward infinity. The mathematics did not merely disagree with experiment, it produced results that could not exist in the real world. It predicted infinite energy, not as a poetic exaggeration, but as a literal outcome of the formulas themselves. Nothing in nature behaved this way. No heated object, no matter how hot, unleashed an endless, world-destroying blast of ultraviolet radiation. The equations were internally consistent, yet profoundly wrong in their conclusions. The mismatch was so stark that it earned a blunt and haunting name, the ultraviolet catastrophe. It was as if the laws of physics, which had worked so perfectly for the motion of the stars and the steam engine, had suddenly run into a brick wall made of light. Physicists tried to fix it without abandoning their familiar ideas. They refined their assumptions, adjusted their models, and scrutinized their experimental setups with desperate care. But no amount of careful tuning could rescue the predictions. The failure did not come from careless measurement or flawed logic. It came from pushing classical ideas into a regime where they no longer applied. Something about the picture of energy itself was breaking down at very small scales. For a time, this failure lingered as an irritation rather than a total crisis. It was uncomfortable, but it was also isolated. The rest of physics worked too well to suggest that the entire framework was in danger. Surely this was just a technical problem, a small knot in the thread that would be smoothed out with the right mathematical insight. But as the sun set on the 19th century, the ultraviolet catastrophe remained a dark cloud on an otherwise clear horizon. It was a silent witness to the fact that the smooth universe was an illusion born of looking at things from a distance. Up close, in the tiny vibrations of atoms and the frequencies of light, the world was preparing to reveal a much more jagged, stepped reality. Think how we perceive a distant hillside. From miles away, it looks like a continuous velvet slope of green. We assume that we could walk up it and move our foot by any tiny fraction of an inch we chose. This is how classical physics viewed energy, as a continuous slope that could be divided infinitely. You could have a little bit of energy, or a tiny bit less, or a tiny bit less than that, forever. But the ultraviolet catastrophe was the first hint that if you got close enough to that hillside, you would find it wasn't a slope at all, it was a staircase. And if you tried to treat a staircase like a smooth slope, eventually, your calculations would fall apart. You would find yourself stepping into empty air where you thought there was solid ground. This realization was terrifying to the scientific mind of the 1890s because it threatened the very idea of continuity. If energy wasn't continuous, if light couldn't be divided forever, then the entire clockwork universe was a lie. The math was screaming that the infinite was impossible, yet the classical laws required the infinite to function. This was the Breyer. This was the moment the gears of the old world began to grind and seize. As the objects around you tonight remain still and warm, they are quietly radiating energy in a way that defies those old broken equations. They are glowing in the infrared, a soft, invisible warmth that follows a new set of rules we were only just beginning to guess at. The catastrophe was necessary because it cleared the path for a new kind of thinking. It showed us that we cannot simply scale up our everyday experiences and expect them to hold true in the heart of an atom. As you drift closer to sleep, consider the irony of this moment in history. The greatest minds of the time were frustrated by a simple glow, a thermal hum that wouldn't follow the rules. They wanted a world of perfect, infinite curves, but they lived in a world of finite, discrete steps. The break wasn't a failure of science. it was an invitation to a deeper truth. The ultraviolet catastrophe was the darkness before the dawn of the quantum age. It was the universe politely informing us that it had limits, and that those limits were the very thing that made life, light, and stability possible. Without the catastrophe, we might never have looked deep enough to find the quanta, the little packets of reality that keep the energy from racing to infinity and keep the world exactly as it should be. The old physics broke so that the new physics could breathe. The failure of the old world to explain the simple glow of heat left a void that could not be filled with familiar logic. It was into this silence that Max Planck entered, a man whose very nature seemed at odds with the revolution he was about to trigger. Planck was not revolutionary by temperament. He was methodical, cautious, and deeply committed to the classical worldview that had defined his education and his career. He did not believe that physics required a fundamenta, overhaul, nor did he set out to dismantle the elegant structures built by those who came before him. His aim was modest and practical, born of a physicist's innate desire for order. He simply wanted the equations describing blackbody radiation to match what experiments were clearly showing. He wanted to fix the broken curve of the ultraviolet catastrophe and restore harmony to the laboratory. Faced with mathematics that refused to behave, Planck found himself pushed into a corner where ordinary adjustments were no longer sufficient. He spent years scrutinizing the thermodynamics of light and heat, searching for a way to bridge the gap between theory and reality. When every traditional path led to a dead end, Planck made an unusual and desperate move. Instead of adjusting the equations further, he decided to adjust the assumptions beneath them. He began to wonder if the problem lay in the very definition of energy. For centuries, energy was treated as a continuous fluid, something that could be poured, measured, and divided into any arbitrary amount. But what if energy could not be exchanged in these infinite, smooth gradients? What if it arrived in discrete steps? To make the numbers work, Planck introduced a daring concept, the idea that energy might be transferred in tiny packets, each with a fixed size. Rather than flowing smoothly like water from a tap, energy would be closer to counting coins. You could have one coin, or two, or three, but you could not have half a coin. This idea of quantization was introduced not as a bold claim about the nature of reality, but as a formal device, what Planck himself called an act of despair. He treated it as a mathematical convenience, a way to force the equations into agreement with observation. To set the scale of these packets, he introduced a small constant, a number that would eventually become one of the most famous UEs in all of science. Its value was extraordinarily tiny, so small that it seemed unlikely to matter beyond this specific, irritating problem of glowing objects. When Planck recalculated the radiation curve using this assumption of discrete packets, the catastrophe vanished. The impossible surge toward infinite energy disappeared. The predictions aligned with the experimental data with a precision that was both stunning and slightly unnerving. The runaway energy was gone, replaced by a curve that bent gently, exactly as nature intended. The equations finally matched the real world, and for the first time, the mystery of the blackbody glow was solved. Yet, despite this triumph, Planck did not trust his own solution. He regarded quantization as a temporary patch, a mathematical trick that had worked but surely didn't reflect the true heart of the universe. He believed that a deeper explanation would eventually be found, one that would restore continuity to physics and render his jerky, stepped packets unnecessary. The universe, Planck felt, surely did not operate in abrupt, jerky steps. The packets were scaffolding, not the final structure. He spent years trying to find a way to derive his formula back into a continuous classical framework, hoping to prove that the packets were just a statistical illusion. From our modern perspective, it is tempting to view this moment as the birth of quantum theory, a dramatic turning point where the light of a new age was suddenly switched on. But at the time, it felt far less significant to the man at the center of it. There were no bold proclamations, no sense that the foundations of certainty had cracked. There was simply a problem that had been fixed in the most economical way possible. Planck published his result quietly, presenting it as a careful piece of mathematical work meant for a specialized audience. Others took note of course, appreciating that the equations finally behaved, but few immediately grasped the deeper implications. After all, classical physics still worked beautifully in almost every other context. The interpretation could wait, but the assumption could not be confined to one corner of physics for long. If energy exchange was quantized in heated objects, why not elsewhere? The question hung in the air like a whisper. Why should atoms absorb and emit energy smoothly if radiation itself did not? Why should light interacting with matter respect continuity when heat refuses to do so? Gradually, similar patterns began to appear in other experiments, hinting that Planck's reluctant assumption might reflect a universal truth rather than a local quirk of thermodynamics. The failure of classical ideas at these small scales was not a failure of human intelligence, it was a failure of extrapolation. Concepts shaped by our everyday experience of the world, like the way a ball rolls or a river flows, had been extended beyond their natural limits into a realm where they no longer held power. At the human scale, energy changes appear smooth because the steps, defined by Planck's tiny constant, are far too small to notice. When you walk across a room, you do not feel the discrete jumps of your motion because the scale of the quantum is billions of times smaller than your stride. But at the scale of an atom, those steps are everything. The universe, it seemed, was counting. This secret counting did not disrupt the beauty of a sunset or the warmth of a fire, but it meant that the world was built on a foundation that was fundamentally different from what we had imagined. Planck himself remained cautious for the rest of his life, often resisting the more radical interpretations that younger physicists would soon propose. He had opened a door that he wished he could close, revealing a world that was grainy and digital rather than smooth and analog. At this early moment, however, none of that was obvious to the world at large. There was only a glow that had refused to behave, equations that had misbehaved in response, and a careful physicist who adjusted the rules just enough to make sense of the measurements. The first crack in reality did not announce itself loudly with a crash. It appeared as a small, quiet assumption tucked into a calculation that erased an impossible result. As you rest tonight, let the image of Planck's packets settle in your mind. Think of the world not as a solid, continuous mass, but as a fine mist of individual events, each one contributing its own small packet of energy to the whole. There is a strange comfort in the idea that the universe is not infinitely divisible, that there is a bottom floor to reality, a minimum unit of being that keeps everything in balance. The steps are small, the packets are light, and the rules are precise. We are moving away from the infinite and into the specific. The world is made of pieces, and those pieces fit together in a way that allows for warmth, light, and eventually life. Planck's reluctant step was the first move into a larger, deeper story, a story that tells us that even the most solid structures are built from a quiet, discrete rhythm. The packets are there, waiting in the stillness, holding the energy of the world in check, allowing the night to be calm and the stars to shine with a light that is counted, packet by packet, as it crosses the dark to find you. Light has always felt gentle. It fills rooms without asking permission, slips through windows, and quietly makes the world visible. Long before anyone tried to describe it with equations, light was treated as something smooth and continuous, more like a ripple spreading across water than a collection of individual things. By the late 19th century, this intuition had hardened into certainty. Light was understood as a wave, and a remarkably well-behaved one at that. It bent, it spread, it interfered with itself, and every careful experiment seemed to confirm that picture. Classical physics was very comfortable here. Waves were familiar territory. Water waves, sound waves, vibrations along a string, all behaved in ways that could be captured cleanly by mathematics. Light fits neatly into that family. Its color depended on frequency, and its brightness depended on intensity. If you make the wave taller, the light grows brighter. If you change the frequency, the color shifts. The relationship felt natural, almost obvious, and perfectly elegant. The trouble began when physicists stopped asking how light moved through space and started asking how it interacted with matter. One experiment in particular refused to cooperate, no matter how carefully it was performed. It involved shining light onto a metal surface and observing what happened to the electrons inside. Under the right conditions, electrons would be ejected from the metal, springing free as if nudged loose by the incoming light. This became known as the photoelectric effect. At first glance, it seemed straightforward. Light carries energy. Energy transfers to electrons. Electrons escape. If you increase the brightness of the light, more energy should be delivered, and the electrons should come flying out with more speed. That expectation, however, turned out to be entirely wrong. What the experiments revealed was strangely precise and deeply confusing. Below a certain frequency of light, no electrons were emitted at all. It didn't matter how bright the light was. You could shine a massive blinding red light on the metal for hours, and the electrons would remain perfectly still. Turning up the intensity changed nothing. The ME tau remained unaffected. Then, if you increase the frequency slightly, shifting toward blue or ultraviolet light, the electrons would be released immediately. Even if that high-frequency light was very faint, the electrons jumped out the moment the light hit the surface. There was no waiting period, no gradual buildup of energy. The effect either happened at once, or it did not happen at all. This behavior was deeply uncomfortable for the wave picture of light. If energy arrived continuously, like a steady stream of water, even dim light should eventually deliver enough energy to free an electron. But time did not help. Brightness did not help. Only color, frequency seemed to matter. Into this puzzle stepped a young Albert Einstein. In 1905, Einstein was not yet the global icon we know today. He was a young physicist working in a Swiss patent office, far from the centers of academic authority. He had been thinking carefully about Max Planck's earlier work on blackbody radiation and the strange suggestion that energy might be exchanged in discrete packets. While Planck had treated that idea cautiously, Einstein recognized that it might reach further than anyone expected. He made a leap that changed the course of science. What if light itself arrived in packets, not just the energy exchanged during heating, but light in its very essence as it interacted with matter? Instead of a smooth wave delivering energy gradually, Einstein proposed that light might come in individual bundles, each carrying a fixed amount of energy determined solely by its frequency. With that shift, the photoelectric effect fell neatly into place. Brightness now controlled how many packets arrived, but not how energetic each individual packet was. A bright, low-frequency light delivered many packets, but each one carried too little energy to free an electron. No matter how many arrived, none would succeed, much like 1,000 gentle ripples failing to knock over a heavy stone. A dim, high-frequency light delivered fewer packets, but each one carried enough energy to do the job. A single interaction was enough. The electron did not slowly accumulate energy over time. It received its gift of energy all at once, in a single step, or not at all. Einstein called these packets light quanta. Later, they would be called photons, but even that word can mislead if taken too literally. A photon is not a tiny marble racing through space. It is the smallest possible exchange of light energy. Light can still spread like a wave while it travels through the void. It can diffract, interfere, and overlap with itself in ways that only waves can. But when it gives up its energy to matter, it does so in whole steps. No fractions, no partial exchanges. Again, the universe revealed a preference for counting. This did not overturn the wave picture of light entirely. Rather, it added a new layer of complexity. Light behaved like a wave when it moved through space, and like a collection of packets when it interacted with matter. Both descriptions were necessary, each illuminating a different aspect of the same phenomenon. Einstein's proposal was bold, but it was firmly grounded in laboratory evidence. The photoelectric effect behaved exactly as the packet idea predicted, and further tests continued to confirm this strange duality. In 1921, Einstein was awarded the Nobel Prize in Physics. Interestingly, it was not for his theory of relativity, which had already begun to transform our understanding of space and time, but for this specific explanation of how light ejects electrons from metal surfaces. Light, it turned out, didn't merely flow, it arrived. This distinction quietly reshaped the entire foundation of physics. Brightness came to mean quantity, the number of photons hitting a surf. Frequency came to mean capability, the energy each photon possessed. One determined how many interactions occurred, while the other determined what those interactions could actually accomplish. Once seen clearly, the difference could not be ignored. It was as if the universe had been whispering a secret about its granular nature, and Einstein was the first to truly listen. In everyday life, nothing seemed to change. Lamps still glowed smoothly, sunlight still warmed the skin, light still appeared continuous to our limited senses. The packets were too small and the steps too fine to notice without the aid of careful clinical experiments. But beneath that smooth surface, the counting continued. Each interaction between light and matter occurred as a discrete event, precise and indivisible. Each freed electron testified to a simple rule that nature appeared unwilling to bend. Energy arrives in steps, and light, however gently it may appear to flow, keeps track of every single one of them. We began to see light not as a chaotic surge, but as a gift delivered in specific portions, a series of interactions that hold the world together through their very precision. As you drift closer to sleep, consider the quiet rhythm of these light packets. Think of the starlight traveling through the vast cold of space, moving as a wave, stretching across billions of miles, only to arrive at your eye and deliver its energy in a single tiny quantum jump. There is deep beauty in this economy of nature. It is a world where nothing is wasted, where every interaction has a cost and a consequence. The universe is not a blurred mess of energy, it is a meticulously organized collection of events. Light is a wave that carries itself with grace, but it is also a particle that acts with purpose. Einstein's insight allowed us to see that even the most ethereal substance in the cosmos has a star, a bottom floor, a limit. The light is counted, the energy is measured, and as the photons find their way to you tonight, they carry with them the quiet logic of a universe that is both a boundless sea and a collection of precious individual moments. At first glance, the double-slit experiment looks almost too simple to matter. It requires only a source of light, a barrier with two narrow openings, and a screen placed behind it to catch whatever makes it through. Nothing about this modest arrangement suggests that it should unsettle centuries of intuition or quietly reshape how reality itself is described. It feels more like a tidy classroom demonstration than a moment that would fundamentally challenge our understanding of space and time. And yet, this simple setup turned out to be one of the most revealing experiments ever performed, exposing a truth about the universe that is as beautiful as it is strange. To understand why this experiment is so profound, it helps to begin with waves, because waves were exactly what everyone expected to see when the test was first conceived. When a wave passes through a narrow opening, it does not simply travel in a straight line, it spreads out. Water waves do this as they move through a gap in a pier, and sound waves do it as they slip through a doorway. Light waves, long understood to behave the same way, also spread as they pass through narrow gaps. If there are two openings instead of one, the waves emerging from each gap overlap with one another. In some places, the peak of one wave meets the peak of another, reinforcing each other to create a stronger signal. In other places, a peak meets a trough and they cancel each other out. This overlapping produces a pattern of alternating bright and dark regions known as interference. On a screen, it appears as a series of evenly spaced bands, a visual fingerprint that waves leave behind wherever they meet and mix. When light is shone through two narrow slits, this interference pattern is exactly what appears. It is a clear and repeatable result that leaves little room for doubt. Light is behaving like a wave. For a long while, that seemed to be the end of the story. The puzzle only deepened, however, when physicists asked what would happen if the light were made extremely faint. Imagine sending light toward the slits one photon at a time, with long pauses in between each shot. Each photon arrives alone, with no neighbors close enough to interact with in any ordinary sense. If light were truly behaving as a stream of particles, like tiny marbles, the expectation would be simple. Each photon would pass through one slit or the other, strike the screen, and leave a single dot. Over time, those dots should form two loose clusters directly behind the slits. But that is not what happens when the experiment is performed. The screen does fill with dots, one by one, each arrival separate and unremarkable. But as the dots accumulate by the thousands, a familiar structure slowly emerges from the randomness. Bright regions appear where many dots land, and dark regions form where almost none do. It is the same interference pattern seen with a continuous beam, a wave pattern built patiently out of individual, isolated events. This result is difficult to absorb at first. Each photon arrives on its own, with nothing else present to interfere with, and yet the overall distribution looks exactly as if waves had passed through both slits and overlapped with themselves. Somehow, each photon contributes to a pattern that seems to require the presence of many possibilities at once. The natural question follows almost immediately. How does a single photon know where to land to preserve the pattern? It does not behave like a tiny marble choosing a single path and a single destination. Instead, it behaves as if its journey between the source and the screen is described by a range of possibilities rather than a fixed route. The photon does not travel along one definite line in the everyday sense. Instead, it evolves in a way that allows many potential outcomes to exist together, each with its own likelihood. The interference pattern is not created by photons bumping into one another. It is created by the structure of those possibilities interfering with themselves. So far, the behavior is strange, but the rules remain consistent. The real tension appears when we try to catch the universe in the act. Imagine a detector is placed near the slits, capable of determining which opening each photon passes through. We want to see which path the particle actually takes. Nothing else in the experiment is changed. The light source is the same, and the screen is the same. Only the possibility of knowing the path is introduced. The effect of this observation is immediate and unmistakable. The interference pattern disappears. The photons now behave exactly like particles, forming two simple clusters behind the slits. Remove the detector and the interference returns. Restore it and the pattern vanishes again. The shift is sharp and absolute. It can feel as though reality is responding to being watched, changing its behavior because it is under observation. But the truth is more grounded. What matters is not awareness, but interaction. To determine which slit a photon passes through, the photon must interact with something physical. That interaction links the photon to the measuring device and, through it, to the surrounding environment. In doing so, it alters the conditions that allow the different possibilities to overlap. When no path information exists, the photon's behavior is described by a broad range of overlapping possibilities. When path information exists, even in principle, those possibilities are narrowed, the overlap is lost, and the interference pattern fades away. The universe is not responding to our curiosity, it is responding to contact. This distinction helps explain why the result feels so counterintuitive to us. Our everyday experience trains the mind to expect objects to have definite positions and paths at all times. A thrown ball follows a clear trajectory. It doesn't explore multiple versions of the air before landing. But at very small scales, that intuition no longer applies. In the double-slit experiment, the pattern on the screen is a map of likelihoods. It is a record of where photons are more or less likely to arrive when the system is allowed to evolve freely without being pinned down. Each detection event looks ordinary, just a single dot, but together they reveal a deeper structure of probability. It is like watching rain fall on a pavement. One drop tells you nothing, but thousands of drops reveal the dry outline of a car that was parked there. Measurement in this setting is an active physical process. By asking a specific question, the system is forced into a more specific state. Specificity comes at a cost. When left alone, reality is generous with its possibilities, but when constrained, it commits to one. This does not mean the world is chaotic. The rules are clear, even if they are not what our intuition expects. The interference is the clue that something wave-like is always present in the background, even when individual events appear particle-like at the moment of detection. The lesson is that the categories of wave and particle are merely tools, not absolute truths. They are useful descriptions that work in some situations and fail in others. When light moves freely, it behaves as if it is everywhere it could be. When it is forced to account for itself, it behaves as if it has always been somewhere specific. Both descriptions are accurate within their limits, but neither tells the whole story alone. Left alone, the universe carries many versions of a story at once. Only when we step in to read the page does it settle on a single sentence. As you settle into the quiet of the night, imagine those countless paths stretching out in the dark, a boundless map of likelihoods, waiting patiently to become real. In this stage of our journey, we must confront one of the most persistent myths of the quantum world, the idea that reality requires a conscious mind to watch over it before it can decide how to behave. It is a tempting and dramatic thought, the notion that the universe sits in a state of fuzzy hesitation until a human eye looks through a lens or a human mind registers a result. But the truth revealed by the double-slit experiment and the study of quantum measurement is something far more physical and, in its own way, far more poetic. The transition from a world of many possibilities to a world of a single, definite outcome is not driven by awareness but by contact. It is a story about the cost of interaction, a quiet tax the universe collects whenever one part of reality touches another. To understand this, imagine a single photon drifting through the dark, headed toward the two slits we explored in our previous chapter. As long as that photon is left entirely alone, it exists as a wave of probability, exploring every path available to it. It is isolated, untouched, and therefore free to be in many states at once. But isolation is a fragile thing. To find out which path the photon took, we must bounce another particle off it, or catch it in a detector, or interfere with its flight in some measurable way. The moment we do this, the isolation is shattered. We have made contact. By touching the photon to learn its secret, we have linked its fate to our own world of large, solid objects. This link is what we call measurement, and the cost of that link is the loss of the photon's fluid, wave-like nature. This process is known in physics as decoherence. It is the bridge between the strange, ghostly world of quantum and the sturdy, reliable world we experience every day. Think of a single, perfect snowflake falling in a dark, silent forest. As long as it stays in the cold, still air, it retains its intricate crystalline symmetry. But if you reach out to touch it, even with the lightest finger, the warmth of your hand and the pressure of your skin instantly change the snowflake. It melts or breaks, losing its delicate structure to become a simple drop of water. The snowflake did not change because you were watching it. It changed because you interacted with it. Your very presence, the heat and mass of your body, was too much for the snowflake's isolation to survive. The universe is constantly touching itself in this way. Every atom in your body, every molecule in the air around you, and every grain of sand on a distant beach is in a constant state of interaction. They are bumping into one another, exchanging heat, scattering light, and pulling on each other with gravity. Each of these tiny collisions is a form of measurement. Each one is a contact that forces a quantum system to account for itself, to settle into a definite position or state. This is why the chair you are sitting in does not behave like a wave. It is far too large and far too noisy to remain isolated. It is being measured trillions of times every second by the air molecules hitting its surface and the photons of light bouncing off its frame. The cost of being a large solid object is that you are constantly being nudged out of the world of many possibilities and into the world of a single fixed reality. We often think of the act of looking as a passive thing, as if our eyes were simply open windows through which the world flows. But in the quantum realm there is no such thing as a passive observer. To see is to interact, to measure is to disturb. If you want to know where an electron is, you must hit it with a photon of light. But that photon carries energy, and that energy will knock the electron off its path. It is like trying to find a balloon in a dark room by swinging a stick. The moment you find it, you have moved it. This is the fundamental limit of our knowledge. We cannot know the universe as it is in total isolation because the very act of trying to know it requires us to break that isolation. We are part of the system we are trying to study, and our contact leaves a permanent mark. This realization brings a certain quietness to the way we think about matter. It suggests that the sharp edges of the world are not its natural state, but a consequence of its interconnectedness. Reality is a vast tangled web of interactions, and it is this very tangling that creates the solidity we lean on. When we speak of the universe responding to contact, we are acknowledging that information is a physical thing. To gain information about a path or a position, energy must be exchanged, and that exchange has consequences. The interference pattern in the double-slit experiment disappears not because the photon knows it is being watched, but because the path information has leaked out into the environment. The wave has become entangled with the detector, the wires, and the air, and in that entanglement, the delicate overlap of possibilities is drowned out by the noise of the macroscopic world. As you lie still tonight, consider the profound silence of the truly isolated. Deep in the heart of a vacuum, or in the frozen reaches of interstellar space, there are particles that may go for long periods without touching anything else. In those moments of total solitude, they are free to exist in that shimmering quantum state, being many things and being in many places all at once. They are the only parts of the universe that truly possess the luxury of boundless likelihood. But here, in the warmth and density of our world, contact is unavoidable. We are part of a grand, ongoing conversation of matter and energy. The cost of interaction is high. It robs the universe of its most exotic behaviors. But the reward is the world itself. Without this constant measurement by the environment, there would be no stable atoms, no solid ground, and no reliable flow of time. The very things that make the quantum world feel so strange are the things that would make our own world impossible to inhabit. We need the universe to respond to contact. We need it to settle into definite shapes and predictable paths so that we can exist within it. The transition from the quantum to the classical is a gentle, relentless process of settling down, a narrowing of focus that allows complexity to emerge from the fog of probability. Let the weight of your body against the bed remind you of this contact. You are being measured by the gravity of the earth, by the pressure of the mattress, and by the air moving in your lungs. You are firmly anchored in the world of the definite. The soft edges of the quantum are still there, deep within the atoms of your being, but they have been quieted by the sheer scale of your existence. There is a peacefulness in this anchoring. You do not have to worry about exploring every possible path or being in 1,000 places at once. The universe has made contact with you, and in that contact, it has given you a place to rest. The science of the small is a reminder of the freedom that exists in isolation, but the reality of the large is a celebration of the stability found in connection. The world is solid because it is touched, and tonight you can let that solidity hold you as you drift away from the questions and into the quiet, certain dark. As the strange results of experiments continued to accumulate, it became clear that physics needed a new way of speaking. Not just new ideas, but a new kind of language altogether. Light behaved like waves until it did not. Particles left individual marks while somehow building wave patterns. The familiar tools of classical motion, neat paths traced through space and time, were no longer enough to describe what was being seen. What was missing was not intuition, but structure. That structure arrived in the form of a mathematical framework developed by Erwin Schrödinger, a physicist who hoped, perhaps optimistically, to restore some sense of continuity to the quantum world. His aim was not to make reality stranger, but to describe it more gently, using smooth change rather than abrupt jumps wherever possible. What emerged from this effort was an equation that would become central to quantum physics, not because it offered easy answers, but because it offered a consistent way to track how quantum systems evolve. It is often called Schrödinger's equation, but thinking of it as a formula to be solved misses its real role. It is better understood as a set of instructions. Given a quantum system as it is now, the equation tells how that system changes over time, not where a particle will be found and not what outcome will occur, but how the range of possibilities reshapes itself moment by moment. At the heart of this description is wave function. Despite its name, the wave function is not a physical wave rippling through space. It does not slosh or vibrate or carry substance from one place to another. It is a description, a compact mathematical summary of everything that can be aid about a system's possible states. It describes where a particle might be found, how likely each possibility is, which energies are allowed, and which outcomes are forbidden. The wave function does not tell a particle where it is, it tells the universe where the particle could be. This shift is subtle but profound. In classical physics, motion is described as a sequence of positions. At each moment, an object occupies a specific point in space and moves smoothly to the next. Given enough information, the entire path can be traced in advance. Uncertainty, when it appears, usually reflects missing knowledge rather than a limitation of nature itself. In the quantum world, that picture dissolves. Instead of a single path, a particle is described by a spread of possibilities, a probability cloud rather than a line. Some regions are more likely than others, but none are guaranteed until an interaction occurs. Between measurements, the particle does not travel from one definite place to another in the familiar sense. Its wave function evolves, reshaping the landscape of likelihoods as time passes. This does not mean the particle is vague or ill-defined. It means the description has changed. Precision now applies to probabilities rather than positions. Schrödinger's equation governs how these probability clouds move and change. It tells how they spread, how they shift, how they interfere with themselves, and how they respond to forces. Importantly, it does it all smoothly. There are no sudden jumps in the evolution of the wave function itself. The mathematics is calm, continuous, and exact. Uncertainty only appears when a specific outcome is demanded. This distinction is often overlooked. Quantum physics is not unpredictable because its laws are sloppy. The laws are precise to an extraordinary degree. Given a wave function, its future evolution can be calculated exactly. What cannot be predicted is which single outcome will be realized when a measurement takes place. That randomness is not a flaw. It is a feature of how the world resolves itself. To understand this, it helps to think again in terms of clouds rather than paths. Imagine releasing a faint mist into still air. The first is concentrated in one place. Over time it spreads, thinning in some regions and thickening in others, depending on subtle currents. The mist does not follow a line, it occupies a region with varying density. A probability cloud behaves similarly. Where the cloud is denser, the particle is more likely to be found. Where it is thinner, it is less likely. But until interaction occurs, the cloud itself is the fullest description available. When a measurement happens, the cloud does not slowly narrow, it resolves into a specific outcome. The particle is in one place with one value of energy or motion. The probabilities have done their job. One possibility has been realized. Before that moment, asking for a precise position is like asking for the exact location of a sound before the instrument is even played. The question does not yet apply to the reality of the situation. This reimagining of motion can feel unsettling because it challenges deeply ingrained habits of thought. Everyday experience insists that objects are always somewhere, moving along well-defined routes whether anyone looks or not. That intuition works beautifully at large scales where probability clouds are so tightly packed that they behave like solid points. At small scales, the clouds are wider and their spread can no longer be ignored. The wave function does not represent ignorance, it represents completeness. It is not hiding a secret path behind a curtain, it is telling the entire story that nature allows at that scale. Trying to force a sharper picture onto it does not reveal more truth. It introduces confusion. This is why it matters to treat the wave function as a description, not an object. It is not something a particle carries around. It is not a physical mist-filling space. It is a rulebook for how possibilities behave. Different interpretations of quantum physics disagree about whether the wave function should be considered real in some deeper sense, but all agree on its practical role. It predicts experimental results with astonishing accuracy. It explains why atoms are stable, why certain energies appear and others do not, and why particles can behave in ways that no classical object ever could. Most importantly, it replaces the idea of fixed paths with something more flexible. Motion at the smallest scales is no longer about tracking where something is at every instant. It is about tracking how likelihoods flow. A particle moves not because it follows a line, but because the center of its probability cloud shifts. Its behavior emerges from the changing shape of possibility itself. In many situations, these clouds remain tightly confined. Their motion closely mimics classical trajectories, which is why the everyday world feels so solid and predictable. In other situations, the clouds spread, overlap and interfere, producing effects that have no classical counterpart. Mathematics allows for both without contradiction. Schrödinger himself hoped that this wave-based picture would soften the harsher edges of quantum theory, restoring a sense of continuity that the idea of sudden collapses seemed to threaten. In some ways it does. The evolution of the wave function is gentle, lawful and smooth. The strangeness enters not through the mathematics but through what is asked of it. When no specific outcome is required, the universe is content to carry many possibilities at once. When an outcome is demanded, one is selected and the rest fall away. Mathematics does not say why that particular outcome occurs, only how likely it was. This is not a failure of explanation, it is a statement about the structure of reality. At the smallest scales, the universe does not commit itself to a single story until interaction forces the issue. Until then, it moves through a space of possibilities guided by precise rules that favor some outcomes over others. Solid paths give way to probability clouds. Deterministic motion gives way to evolving likelihoods. What replaces certainty is not chaos, but a calmer, subtler order. The mathematics of possibility does not strip meaning from the world, it reshapes it, and in doing so, it offers a picture of motion that is less rigid, more flexible, and in its own way deeply elegant. As you drift tonight, imagine the universe not as a collection of hard points, but as a series of instructions unfolding in the dark, a smooth, continuous wave of what might be, moving gently toward what will be. The transition from the rigid world of moving points to the fluid world of probability clouds marks the moment where human intuition must truly bow to the reality of the small. In our everyday experience, we are masters of the definite path. When we watch a bird fly across the sky or a car drive down a street, our minds automatically trace a line for them. We assume that at every fraction of a second, that object is at one specific measurable point and that it moves to the next point in a continuous unbroken chain. This is track comfort. It allows us to predict where the ball will land and where the sun will rise, but as we descend into the microscopic, this line, this definite path, begins to fray and eventually dissolves altogether. It is replaced by something much more ethereal, the probability cloud. To understand the end of the definite path, we must first accept that the blur of the quantum world is not a result of poor eyesight or bad instruments, it is the natural state of things. When we speak of a probability cloud, we are describing a region of space where a particle, like an electron, is likely to be found. But the word likely here is doing a great deal of work. In the classical world, if I say a key is likely in your pocket, it means the key is definitely in one spot, and I simply don't know which spot it is. In the quantum world, saying an electron is likely in a certain region means the electron itself has not yet committed to being in any one spot. It is, in a very real sense, sprawling. It exists as a presence throughout the cloud, a shimmering field of potential that refuses to be a single dot until it is forced to interact with something else. This shift changes how we must think about the very nature of existence. If a particle does not have a definite path, it means it is not traveling in the way we understand travel. Instead of a bead moving along a wire, imagine a sound moving through a room. You cannot say the sound is at one specific coordinate. It is a volume of vibrating air. It has a center where it is loudest and edges where it fades, but it occupies the whole space at once. The probability cloud is the sound of a particle's existence. Schrödinger's equation, which we explored previously, acts as the conductor for this sound, telling the cloud how to pulse, how to expand, and how to shift its weight from one side to the other, but it never tells the particle to become a single point. That only happens when the music stops. At the moment of measurement, the end of the definite path is also the end of the idea that we can know everything about a system at once. In the macroscopic world, we can know where a train is and how fast it is going. In the microscopic world, the more we try to pin down the where, the more the how. Fast begins to blur, and vice versa. This is because the probability cloud has a specific shape and size. If you try to squeeze the cloud into a tiny, definite point to find its exact position, the cloud reacts by becoming extremely restless. The energy within it surges, and the velocity becomes a wild range of possibilities. The universe seems to insist on a certain amount of fuzziness. It refuses to let us have both a perfect point and a perfect path. It demands that we accept the cloud as the fundamental reality. Consider the atom, the building block of everything you see. Old textbooks used to draw atoms like miniature solar systems, with electrons orbiting the nucleus like planets orbiting a sun. This image is easy to understand, but it is fundamentally wrong. If an electron followed a definite circular path like a planet, it would constantly radiate energy and eventually spiral into the nucleus, causing the atom to collapse in a fraction of a second. The reason atoms are stable, the reason you are solid and the stars continue to shine, is because the electron does not follow a path. Instead, it exists as a standing wave of probability, a cloud that wraps around the nucleus in a stable, quiet shell. It is everywhere in that shell at once, and nowhere in particular. It is the cloud-like nature of the electron that prevents it from falling in. The blur is what keeps the universe from collapsing. As you lie in the stillness of the night, think about the atoms that make up your own body. Trillions upon trillions of probability clouds are held in a delicate, rhythmic balance. There are no tiny marbles spinning inside you, there is only a vast interconnected web of likelihoods. Each electron in your skin, your blood, and your bones is a quiet excitation of a field, a soft cloud that knows its boundaries but refuses to be pinned to a single coordinate. This is the true meaning of the end of the definite path. It is a move away from the clockwork universe, where every gear must mesh perfectly, toward a universe that is more like a vast, breathing ocean. In this ocean, things don't happen along lines. They emerge from the depths of probability. This perspective can be deeply soothing if we let it be. The pressure of the definite, the rigid requirement that everything must be exactly one way or another, is a heavy burden we carry in our daily lives. But the universe does not carry that burden. It is content to let things linger in a state of maybe. It allows the cloud to drift and evolve, exploring all the ways it can exist before it finally settles into a single moment. When we stop looking for the definite path, we open ourselves up to the true elegance of the quantum world. We see that the world is not a collection of objects, but a collection of events, and each event is preceded by a beautiful shimmering cloud of what might be. Clouds are no sign of chaos. They obey strict, elegant laws of mathematics. They interfere with one another, creating patterns of reinforcing and cancelling likelihoods. They tunnel through barriers and entangle with distant neighbors. They are the scaffolding upon which the solid world is built. We perceive the world as solid and definite only because we are so large that we see the average of trillions of these clouds all at once. Like looking at a distant forest and seeing a single green mass instead of a million individual leaves, we see things where there are actually tendencies. But tonight, we are looking closer. We are acknowledging the leaves. We are feeling the mist. Let the sharp edges of your own thoughts begin to dissolve into a similar kind of cloud. You do not need to be a single, definite point of worry or calculation tonight. You can allow your mind to become a spread of possibilities, a quiet drift of images and sensations that do not need to lead anywhere in particular. The definite path of your day has ended, and the probability cloud of the night has begun. Just as the electron finds stability in its fuzzy, spread-out state, you can find rest in the loosening of your own certainty. The universe is not a machine, it is a soft, evolving wave, and as the clouds of your atoms continue their silent dance, you are part of that wave, moving gently through the dark, held by the laws of probability in a world that is far more generous and fluid than it first appeared. Even with careful mathematics and beautifully predictive equations, there remained a sense that something fundamental was slipping through the fingers as quantum theory matured. It was not a gap in knowledge that better tools might fix, but a limit that refused to move no matter how gently it was approached. This limit became known as the uncertainty principle, and it has been misunderstood almost from the moment Werner Heisenberg first introduced it. At first hearing, it sounds like a confession of failure. It is often presented as a statement that measurements are clumsy, that our instruments interfere too much with the world, and that precision is lost because the act of looking gets in the way. People imagine that if we shine light to see a particle, the light knocks it about, or if we try to pin down its motion, the act of pinning disturbs it. From this point of view, uncertainty feels like an engineering problem, a hurdle that might be cleared by a future generation with more delicate sensors. But that explanation, comforting as it may be to our classical minds, misses the profound heart of the matter. The built-in blur is not about the limitations of technology, and it is not about careless measurement. Even in a perfectly quiet universe with perfect instruments and infinite patience, the uncertainty would remain. A clumsy observer does not impose it from the outside. It is woven into the very structure of nature itself. To understand why this is, we must look at what a particle actually is at this scale. A particle described by a wave function does not occupy a single location like a tiny marble. As we have explored, its presence is spread out, more like a probability cloud. It is more here and less there, with no sharp, absolute boundary. That spread is not a blur caused by our ignorance of its real position. It is the most complete description available. Now, imagine trying to squeeze that spread into something narrower. The more tightly you try to confine that cloud in space, the more you insist on knowing exactly where it is, the more complicated its internal structure must become. It begins to vibrate with more energy. It includes a wider range of possible motions. Precision in position comes at an immediate and unavoidable cost to precision in motion. This is not because something has gone wrong in the laboratory, but because waves simply behave that way. This trade-off is a mathematical necessity. It is not a statement about what can be known by a human mind, it is a statement about what can actually exist in physical space. Trying to specify both a perfect position and a perfect motion simultaneously is like trying to describe a melody using only a single, frozen instant of sound. The request itself asks for more than the phenomenon can provide. A single moment of sound has no pitch. Pitch requires time to reveal its frequency. Similarly, a particle requires a certain spread to have a defined motion. The universe does not store the information of a perfect path because that information is not part of how things are organized at the fundamental level. This is why the uncertainty principle feels so different from our everyday experience. In our daily lives, objects appear to have definite positions and definite motions at all times. A car moves down a road with a clear speedometer reading and a clear GPS coordinate. Nothing seems blurry or ambiguous. However, those objects are made of vast, unfathomable numbers of particles. Their individual uncertainties overlap and average out, producing a collective behavior that appears crisp, solid, and deterministic. The blur is still there, tucked away in the foundations, but it is buried beneath the sheer scale of the macroscopic world. At the scale of the single atom, there is nowhere for the blur to hide. A helpful way to picture this is to think of a thick fog in a valley at night. Standing in that fog, you might be able to tell roughly where a light is, but the closer you get to it, the more the light seems to disperse. There is no single vantage point where the light snaps into a perfect, infinitely small point. The fog is not hiding a sharp point of light. The light itself has become a distributed phenomenon within the mist. The fog is the situation. The uncertainty principle expresses a fundamental balance, a cosmic limit that prevents the universe from being pinned down too tightly. One of the most important consequences of this rule is that it rules out certain classical fantasies entirely. There is no hidden ledger beneath the surface of reality where every particle carries an exact position and an exact motion at all times, just waiting for a clever enough scientist to find them. Nature refuses that level of precision because it would make the universe fragile. This refusal is not sloppy or approximate. The boundary that Heisenberg's limit draws is sharp, mathematical, and unyielding. It does not say that nothing can be known. It says that some pairs of properties cannot be defined simultaneously beyond a certain limit, because defining one necessarily loosens the other. Within that limit, quantum physics remains astonishingly predictive. What it does not offer is certainty about individual outcomes, and it never promised to. This built-in blur reshapes how we understand the very concept of happening. In the quantum world, motion is not the steady sliding of a point along a line. It is the evolution of a distribution, a shifting pattern of likelihoods that flows and reshapes itself over time. A particle moves because its probability cloud moves. The center of that cloud may drift, and its shape may stretch or compress, but it never collapses into a perfectly sharp point while retaining a perfectly sharp motion. This blur is not a flaw to be corrected, it is what allows the quantum world to function and remain stable. Without it, the electrons in an atom would have no reason to stay in their clouds. They would be drawn N to the nucleus by electrical attraction, and the entire structure would collapse instantly. Matter would lose its volume, chemistry would fail, and the complexity of life would never have emerged from the void. The uncertainty that feels so uncomfortable to our logic turns out to be the quiet guardian of everything we know. There is a strange kindness in that. What appears as a restriction on our knowledge is actually a protection of our existence. The blur prevents the universe from becoming too rigid. It allows systems to settle into stable arrangements rather than spiraling into extremes of density or energy. At large scales, the uncertainty becomes vanishingly small, and the paths reappear, but the fog remains the foundation. As you drift closer to sleep tonight, consider the peace that comes with this built-in blur. We spend so much of our waking lives trying to pin things down, trying to find the exact position of our problems or the exact trajectory of our futures. We demand a level of certainty that even the atoms themselves do not possess. But the universe is telling us that it is okay to be a little spread out. It is okay for the edges to be soft, just as the electron finds its stability not in a sharp point, but in a distributed cloud. You can find your rest in the loosening of the need to be precisely one thing or in one place. The uncertainty principle is not a wall, it is a cushion. It is the softness at the heart of the world that ensures nothing is ever pinned down too tightly, leaving room for possibility to move. You are made of this softness. Your very being is supported by this fundamental refusal to be rigid. Let the sharp questions of the day lose their focus. Let the trajectory of your thoughts widen into a quiet, peaceful mist. The universe is not a machine that needs every gear to be perfectly aligned. It is a soft, rhythmic pulse that thrives. S on the blur. In this quiet frontier, precision is no longer needed. There is only the gentle, unfocused flow of the night, where the uncertainty is not a lack of knowledge, but a presence of peace. In our journey through the strange landscapes of the quantum world, we often encounter ideas that seem designed to unsettle us. We speak of the end of the definite path and the dissolution of the sharp edge, and it is easy to feel as though we are losing something precious. We have been taught to value certainty, to prize the solid and the fixed, and to see any kind of blur as a sign of weakness or a failure of vision. But as we move deeper into the quiet logic of the microscopic, we discover a profound secret. The uncertainty that felt like a restriction is actually a form of kindness. It is the very thing that prevents the universe from collapsing in on itself. Without the built-in blur, without the refusal of the universe to be pinned down, the world as we know it would vanish in a heartbeat. The stability of every star in the sky and every cell in your body is anchored not in rigidity, but in a fundamental, protective fuzziness that keeps the forces of nature in a state of eternal, gentle balance. To understand why this uncertainty is so kind, we must look at the atom, the tiny architecture that builds the entirety of our reality. In the older classical worldview, we imagined the atom as a miniature solar system. At the center sat the nucleus like a tiny sun, and around it zipped the electrons like planets in tight circular orbits. It was a beautiful, orderly image that fit our love for clockwork machines. But if that image were true, the universe would be an impossible place. An electron is a charged particle, and classical physics tells us that a charged particle moving in a circle must constantly lose energy by radiating light. If an electron were truly a tiny marble, Following a definite sharp path around a nucleus, it would lose its energy almost instantly. It would spiral inward, faster and faster, until it crashed into the center. Every atom in the universe would collapse into a point of infinite density in a fraction of a second. There would be no chemistry, no solid ground, and no life to ask these questions. The reason this catastrophe does not happen is because the electron refuses to be a tiny marble on a definite path. It embraces the uncertainty we once feared. Because of Heisenberg's limit, an electron cannot have both a fixed position and a fixed motion. If it were to be pulled too close to the nucleus, its position would become too well defined and the uncertainty principle would react. The electron's motion uncertainty would surge, giving it a massive kick of energy that pushes it back out. It is as if the electron has a built-in cushion that prevents it from ever being squeezed too tightly. Instead of a planet on a track, the electron exists as a spread-out cloud of probability, a standing wave that finds a stable, quiet shape around the nucleus. It doesn't crash because it is too blurry to fall. This blur is the protector of the atom's volume. It is what gives matter its size and its strength. When you press your hand against a table, you are feeling the combined pushback of trillions of these quantum cushions, refusing to be compressed. This protective nature of uncertainty extends far beyond the individual atom. It is the reason the sun shines, and the reason the stars do not simply burn out in a single, violent flash. In the heart of a star, gravity is trying with all its might to crush the matter into a single point. It pulls every atom toward the center with a weight that is almost unimaginable. In a world of perfect classical certainty, gravity would win every time. But as the matter is squeezed together, the uncertainty principle intervenes once more. The particles, forced into smaller and smaller spaces, gain more and more motion uncertainty. This creates a powerful outward pressure, a quantum resistance that holds back the crushing weight of gravity. The star finds a balance, a long, peaceful equilibrium where it can burn steadily for billions of years. We owe our very existence to this cosmic standoff between the pull of the large and the quiet, stubborn blur of the small. There is a deep peace to be found in recognizing this kindness. We often think of uncertainty as a source of anxiety, a dark space where we don't know what will happen next. But in the physical world, uncertainty is the source of all stability. It is the reason the floor remains solid beneath you, and the reason your heart continues its rhythmic beat. It is the softness that allows the universe to be complex. If everything were perfectly definite, the universe would be brittle, like a glass tower that shatters at the first touch. But because reality is built on a foundation of probability and blur, it is resilient. It can absorb change, it can shift and adapt, it can grow into the vast variety of forms we see around us. The fuzziness is not a lack of order, it is a higher, more flexible kind of order that protects the integrity of the whole. As you settle further into the quiet of the night, let this thought hold you. You do not need to be a perfectly defined, sharp-edged thing to be stable. Much like the atoms that compose you, your strength does not come from being rigid or having every answer fixed in a single point. There is a kindness in letting the edges of your identity and your worries soften. Just as the electron finds its stable home in a cloud of potential, you can find your rest in the realization that you are supported by a universe that thrives on the undefined, the press. You are to be certain to have a definite path and a perfect trajectory is a human invention that does not reflect the deeper laws of nature. The stars are not anxious about their paths. They are held in a gentle, probabilistic dance that has lasted for eons. Consider the silence of the room. It feels empty, but it is saturated with the quiet resistance of the quantum world. The air molecules are jittering with their zero-point energy, never quite coming to a complete rest, held in place by the same rules that keep the atoms in your skin from collapsing. This constant, subtle activity is the true baseline of reality. It is a world that is always breathing, always moving in small, gentle steps that never quite reach a final, frozen end. This is blurry goodness. It keeps the world in motion. It ensures that there is always room for the next moment, the next possibility, and the next breath. The universe is not a finished, static object. It is a living, evolving wave of likelihoods. Tonight, you can release the need to pin the world down. You can let the sharp questions of the day dissolve into the protective fog of the night. The uncertainty principle is not a barrier to our understanding. It is the reason there is a world to understand at all. It is the cushion that protects the small and the pressure that supports the large. As your thoughts expand and lose focus, remember you are made of this same protective softness. Your existence is a celebration of the blur. You are held in a state of eternal rhythmic balance by laws that are as precise as they are gentle. The world will not collapse while you sleep. It is anchored in a kindness that reaches down to the very heart of matter, ensuring that everything remains exactly as it should be, fluid, stable, and full of quiet potential. Let uncertainty be your ceiling tonight. Let the softness of the quantum world be your res. The night is vast, the stars are steady, and the blur is exactly where it needs to be, holding the universe together with a touch that is lighter than a dream. One of the most persistent ideas in everyday thinking is that things must always be one way or another, here or there, moving or still, on or off. It feels natural to assume that reality makes up its mind immediately and then sticks with that decision. At large scales, this assumption works beautifully. A book is either on the shelf or in your hand, a door is either open or shut. But as we descend into the very small, into the quiet, shimmering world of the quantum, that confidence quietly falls apart. In the microscopic realm, systems do not rush to choose a single state. They linger in a state of beautiful, open possibility, carrying several potential outcomes at once. This behavior is known as superposition, and despite its reputation for sounding mystical or absurd, it is best understood as something calm, practical, and deeply ordinary once the right picture is in place. Superposition does not mean that a particle is confused, conflicted, or half-finished. It means that before interaction demands a specific answer, the system is described by more than one allowed state at the same time. These states coexist, each weighted by how likely it is to appear when the moment of truth finally arrives. This coexistence is not a failure of the universe to decide, it is the natural default of a reality that is fundamentally generous with its options. To see why this happens, it helps to return to the idea of the wave function that we have explored in previous chapters. The wave function does not point to a single lonely outcome. It describes a spread of possibilities, each one mathematically present and evolving smoothly over time according to precise rules. As long as the system is left alone, untouched by the outside world, nothing in mathematics forces one possibility to be selected over the others. There is no hidden clock counting down to a final decision. The system does not choose because, in its isolated state, nothing requires it to. In classical physics, change is driven by forces acting on objects with definite properties. Push something and it moves, pull it back and it slows. The present determines the future in a single, continuous, rigid chain. But in the quantum picture, the rules are much smoother. The wave function evolves according to laws as exact as any in science, but those laws govern the landscape of probabilities, not the specific destination of an object. As time passes, the distribution of these possibilities shifts and reshapes itself. Some outcomes become more likely while others fade into the background. But until an interaction occurs, all allowed outcomes remain part of the description. This is what superposition really means. It is the coexistence of futures. A quantum system can be in a superposition of positions, meaning there are several places it could be found if we were to look. It can be in a superposition of energies, meaning it does not possess a single, definite energy until an interaction demands one. These are not vague or messy states. They are sharply defined sets of possibilities, each with its own mathematical weight. The outcomes themselves, once they are realized, are never blurry. When a result finally appears, it is always definite and clear. The blur exists only in the range of options that are held in balance before that moment. This distinction matters deeply because it dissolves many common misunderstandings. A particle in superposition is not physically smeared across space like paint dragged across a canvas. It is not partly here and partly there in the way a cloud of dust is spread out. It is fully capable of being. Found in several different places, and until an interaction occurs, none of those possibilities has been excluded by the universe. It is a state of pure, unmanifested potentiality. Measurement is where the narrowing happens. When a quantum system interacts with something large enough to register an outcome, like a detector, a screen, or even a stray molecule of air, the range of possibilities contracts. One option becomes the reality we perceive, while the others fall away. This is often described as the collapse of the wave function, but that word can suggest something violent or dramatic, as if reality was shattering into place. In practice, the process is much quieter and rhythmic. Measurement does not create an outcome from nothing, it simply selects one from the set that already existed. The system does not invent a new property at the moment of interaction, it merely reveals one that was already allowed. A helpful way to think about this is to imagine a wide beam of light passing through an adjustable opening. Before opening, light spreads widely across many paths. After it passes, the beam is constrained. The light itself has not changed its fundamental nature. The range of paths it is permitted to take has simply been limited by the environment. This perspective removes the temptation to think of observation as something magical or driven by human consciousness. Nothing waits for a mind to notice it. Nothing snaps into place because it is observed by a person. What matters is physical interaction. When a system becomes linked to its surroundings in a way that records an outcome, the superposition can no longer be maintained. The universe does not demand an answer until it absolutely has to for the sake of consistency. This reluctance to choose is not a flaw in the design of the cosmos, it is a profound advantage. By allowing multiple possibilities to coexist, quantum systems can behave in ways that would otherwise be impossible. We see the effects of this everywhere in the micro world. Interference patterns arise because overlapping possibilities can reinforce or cancel one another. Tunneling occurs because the range of allowed states includes outcomes on the other side of barriers that classical objects could never cross. Atomic stability emerges because electrons exist in superpositions that spread them out into stable shells rather than forcing them into tiny, unstable orbits. Without superposition, the quantum world would be brittle and stagnant. Systems would collapse into extremes, and the complex structures of matter would be lost. Even technologies that now feel cutting edge, like quantum computers, rely on this quiet feature of reality. The power of these machines does not come from raw speed alone, but from their ability to allow many possibilities to evolve together, carrying multiple potential answers forward at the same time before narrowing them down to a solution. Nature has been doing this long before humans noticed. We see hints of superposition in the way energy moves efficiently through the complex molecular structures of plants during photosynthesis. These effects are subtle and delicate, but they point to the same underlying principle. Keeping options open is useful for the universe. It allows for a richness and a flexibility that a purely either-or world could never sustain. At larger scales, this behavior becomes difficult to see because interaction happens constantly. Air molecules collide, light scatters, and heat flows in a never-ending stream of contact. Superpositions are narrowed almost immediately by the environment, leaving only one outcome visible to our eyes. This is why everyday objects appear definite and stable. They are never isolated long enough to remain in a state of coexistence. B. At small scales, where isolation is possible, the openness remains. Superposition is often described as strange because it conflicts with the habits we have formed in a classical world. But strangeness is not the same as incoherence. The rules governing superposition are precise, testable, and reliable. The universe does not insist on being only one thing at a time. It allows itself to be many things until interaction demands a choice. As you drift towards sleep tonight, let this generosity of possibility be a comfort to you. You do not need to rush toward a single definite version of your future or your thoughts. Much like the quantum systems that compose you, you can allow your mind to linger in a state of superposition. You can carry multiple feelings, multiple dreams, and multiple thoughts together without the pressure to choose one or discard the others. The night is a time of isolation, a time when the measurements of the day, The demands, the schedules, the interactions begin to fall away. In this quiet space, you are free to explore the breadth of your own potential. You are a wave of possibilities, moving through the dark, held by a reality that is patient and wide. Let the sharp edges of the day soften into the coexistence of the night. Sleep is the moment where we stop demanding answers and allow the universe to return to its natural, shimmering state of both and. The science is certain, the probabilities are weighted, and the futures are all there, waiting quietly in the stillness for the morning to bring them into focus. Distance feels authoritative in everyday life. Two objects close together can influence one another easily. Two objects far apart cannot. Space separates, delays, and protects causality. This expectation is so deeply ingrained that it rarely feels like an assumption at all. It feels like an absolute fact of nature. We believe that or one thing to affect another, there must be a signal, a touch, or a bridge crossing the gap between them. At the quantum level, however, that confidence begins to soften. When two quantum systems interact in certain specific ways, they can become linked so thoroughly that describing one without the other no longer makes any sense. Their properties stop belonging to them individually and begin to belong to the pair as a whole, regardless of how much distance is later placed between them. This linking is called entanglement, and it is not about mysterious forces reaching across space like invisible fingers. It is about relationships that refuse to break when distance is introduced. To understand entanglement, it helps to stop thinking in terms of individual objects and start thinking in terms of shared descriptions. In classical physics, systems carry their own properties wherever they go. If you have two balls, one red and one blue, and you move them to opposite sides of a room, the red ball stays red and the blue ball stays blue. Their states are independent. Quantum systems do not always behave this way. When two particles interact and become entangled, the wave function that describes them no longer splits neatly into two separate parts. Instead, there is a single description that applies to both together. Certain properties, such as their spin or polarization, remain undefined individually, but the relationship between them becomes sharply and perfectly defined. The particles do not each carry a complete set of private instructions. Instructions are shared across the system. Imagine preparing two particles in such a way that when one is found to have a particular property, the other must have a corresponding one to balance the cosmic ledger. The specific outcomes are not fixed in advance, but the correlation is absolute. Whatever happens here must be consistent. Whatever happens there, once the particles move apart, even by light years, that correlation remains intact. This is where deep discomfort begins to creep into our logical minds. If one particle is measured and a result is obtained, the outcome for the distant particle is immediately constrained. The shared description updates in an instant. It can feel as though information has traveled instantly from one location to another, as though space itself has been bypassed or ignored. This impression troubled Albert Einstein deeply. Einstein was not opposed to quantum mechanics as a predictive framework. He was one of its primary architects. But he was uneasy with any picture of reality that seemed to allow influences without mediation through space. For him, locality mattered. Causes should not leap across distance. Nothing should outrun light. Entanglement appeared to challenge that principle. Einstein famously referred to it as spooky action at a distance, not as a compliment, but as a warning that the theory might be missing something fundamental. And yet, careful examination shows that entanglement does not actually violate the rules of relativity. The key is understanding the difference between correlation and communication. When a measurement is made on one member of an entangled pair, the outcome is random. The observer cannot choose or control it. Because the result is random, no message can be sent. The same is true for the distant particle. Its outcome is not caused by the measurement elsewhere in a mechanical sense. It is constrained by the shared structure of the entangled state that existed since the moment of their first interaction. No message is sent through the void. No signal travels between the 2 points. The apparent instant update occurs in the mathematical description of the pair, not through a physical force moving in space, until the results for Both locations are compared, which requires ordinary communication limited by the speed of light. Nothing observable distinguishes entanglement from mere chance. Relativity remains perfectly intact. This distinction is subtle but essential for our peace of mind. Entanglement does not allow control at a distance, it allows consistency at a distance. The universe ensures that outcomes fit together properly, even when they are separated by vast stretches of space. It does this not by sending hidden messages, but by never assigning independent properties in the first place. The correlation was built in from the start, a single story told across two different locations. A common way of explaining this uses the idea of paired objects prepared together and then separated, like a pair of gloves. If you find a left-handed glove in one box, you know the other box contains a right-handed glove. But that analogy only goes so far. In the glove example, the properties were fixed the moment they were created. One was always left and one was always right. In quantum entanglement, the outcomes are not predetermined. The universe commits to the relationship without committing to the individual values until the measurement actually occurs. Consistency is guaranteed, but the specifics are left open until the very last moment. This is what unsettled Einstein. He suspected that hidden details must exist beneath the surface, quietly assigning definite properties ahead of time. However, over decades, experiments were designed to test this possibility. Again and again, the results favored the quantum description over the classical one. Nature appeared to resist being reduced to hidden classical instructions. Entanglement is not rare or exotic. It arises naturally whenever quantum systems interact and then separate without losing their delicate coherence. It plays a silent role in the struct. Of atoms, in chemical bonding, and in the collective behavior of particles in solids. It is not an anomaly, it is part of the basic fabric of the quantum world. It has become a practical resource in our modern age. Technologies like quantum cryptography rely on entanglement for absolute security. Any attempt to intercept or copy an entangled system disturbs it in detectable ways, breaking the spell. The same relational structure that once seemed philosophically troubling has become, in this context, extremely useful. What makes entanglement powerful is not mystery but a deeper form of connection. The impossibility of controlling outcomes at a distance is a feature that protects the integrity of these cosmic correlations. Seen this way, entanglement does not undermine causality, it reframes it. Cause and effect still respect the speed of light, but we must accept that at small scales reality is organized around relationships first, with individual attributes emerging only when interaction demands them. Distance, in this picture, is not the ultimate divider we thought it was. Two particles that were once connected can remain part of a single description even when space grows between them. Their separation does not erase the history of their interaction. The universe remembers how they were linked. Entanglement does not suggest that everything is secretly connected to everything else in a chaotic web. It suggests that when connections exist, they matter deeply and do not dissolve simply because objects move apart. The discomfort surrounding entanglement often comes from trying to force it into classical categories. We want to know if something is moving between particles. We want to know if information is moving. These questions assume that the only way to maintain consistency is through transmission across space. Quantum physics offers another option, consistency C, and be global rather than local. Relationships can be fundamental rather than derivative. Einstein's unease was an honest response to a genuine shift in perspective. He acknowledged something profound was being claimed. Across any distance, the quantum world can maintain relationships that are stronger than separation, ensuring that when outcomes finally appear, they do so in perfect agreement with a structure that was shared all along. As you drift into sleep, let the idea of this spooky consistency be a comfort. You are not a solitary point in a cold, disconnected void. You are part of a universe that values relationship and consistency, a reality where connections endure across the dark, holding the pieces of the world together in a quiet, invisible embrace. The space between us is not just an empty gap. It is a stage for a deeper kind of unity that the night cannot break. There are few images in science as famous or as persistently misunderstood as a cat sealed inside a box. It appears again and again in explanations of quantum physics, often presented as proof that the universe is absurd, paradoxical, or deliberately mischievous. A cat, the story goes, is somehow both alive and dead at the same time, suspended in a strange limbo until someone opens the lid and looks inside. It is a memorable and unsettling image, yet it is almost always presented as a literal claim about how reality behaves. That is precisely why it causes so much confusion. The scenario involving the cat was never meant as a statement about the world. It was a critique, a carefully designed objection meant to expose a problem in how quantum ideas were being interpreted. Schrödinger did not introduce the cat to celebrate quantum strangeness, but to question how far certain explanations could reasonably be pushed before they stopped making sense. He wanted to show that the logic of the very small not be dragged carelessly into the world of the very large without something breaking. To understand what the thought experiment was actually targeting, it helps to return to the unease that motivated it in the 1930s. By then, quantum mechanics had already proven its power. It described atoms with remarkable accuracy and explained how light and matter interact at small scales. And yet, despite this success, something about its interpretation felt unfinished. The mathematics described smooth, continuous evolution through wave functions, while measurements produced single, definite outcomes. Somewhere between those two facts lay a gap that had not been fully explained. Quantum systems could exist in superpositions, carrying multiple possible outcomes at once, but measurements never revealed that multiplicity. They revealed only one result. Schrödinger was troubled by how casually this transition was sometimes set aside. To make the issue impossible to ignore, he proposed an exaggerated scenario that deliberately stretched quantum reasoning into an uncomfortable domain involving a living creature. The setup is simple but stark. A sealed box contains a cat, a tiny amount of radioactive substance, and a device triggered by a single atom's decay. If the atom decays, a hammer breaks a flask of poison, and the cat perishes. If it does not, the cat lives. The atom itself, being a quantum object, can be described as existing in a superposition of decayed and not decayed. If we apply the math of the microscopic world directly to the macroscopic world without any qualification, the cat is forced into a superposition of its own. It becomes entangled with the atom, resulting in a state where the cat is both alive and dead until the box is opened. Schrödinger's point was that this conclusion is clearly ridiculous. A cat is a large, complex object that does not behave like a single atom. By using the cat, he was issuing a warning. The wave function is a tool for calculation, but treating it as a literal physical picture of a cat's life and death leads to nonsense. Much of the misunderstanding comes from blurring the line between measurement and knowledge. It is tempting to imagine measurement as an act of awareness, as if learning the outcome somehow causes the reality to snap into place. Open the box, see the cat, and the universe decides. This framing feels intuitive because it mirrors human experience, but it does not reflect how physics actually works. Knowledge is not a physical process, interaction is. Long before anyone opens the box, the system inside is already interacting relentlessly. The radioactive atom interacts with the detector interacts with the air, and the cat interacts with everything around it. These interactions matter because they entangle the system with its surroundings in a process called decoherence. As this entanglement spreads, the delicate superpositions that can exist in isolated quantum systems become distributed across the environment. Once information about a quantum system leaks out into the world, maintaining a coherent superposition becomes impossible. The outcome becomes definite, not because someone knows it, but because the system has become irreversibly linked to the world around it. By the time the box is opened, the result has already been settled by the physical noise of the environment. Opening the box merely reveals what has already occurred, it does not cause the event. This is where macroscopic intuition fails when applied too directly to quantum ideas. Superposition is not a universal condition that applies to everything equally. It is a fragile state that requires total isolation to persist. The larger and more complex a system becomes, the harder it is to protect it from interactio. A cat is not a single quantum system. It is an enormous, noisy collection of interacting parts that cannot stay quantum for long. Schrödinger's cat serves as a reminder that there is a transition between the world of the small and the world of the large. There is no sharp boundary where the quantum world suddenly switches off, but there is a gradual loss of the both-and logic as systems grow. Large objects are never truly left alone. They are constantly being measured by their surroundings through heat exchange, air collisions, and light. This is why we don't see people in superpositions or cars in two places at once. The cat thought experiment exposes the danger of ignoring this transition. It shows what happens when we treat the wave function as a literal description of a macroscopic object's physical state, rather than a mathematical tool for predicting probabilities. Schrödinger was not arguing that the cat is both alive and dead. He was arguing that if your theory says the cat is both, your theory is missing a piece of the story. The thought experiment also reveals a deeper lesson about the limits of storytelling in physics. Quantum mechanics is not a narrative theory, does not describe what is happening moment by moment in the way classical stories do. It describes relationships and constraints. When those descriptions are forced into familiar story shapes, like the life and death of a pet, paradoxes appear. These paradoxes are created not by nature, but by our misplaced expectations. This does not dissolve every mystery, as questions about the exact nature of measurement remain a subject of deep debate. However, none of the modern approaches require human consciousness to play a magical role. Reality does not wait for a witness, it responds to contact. The universe proceeds whether we are paying attention. As you rest tonight, you can let go of the worry. That reality is waiting on you to define it. The world around you is stable and definite precisely because it is so full of interaction. The floor under your bed is being measured by the weight it carries. The air in your room is being measured by the walls it touches. This constant, quiet conversation between objects keeps the world in focus. You are not suspended in a limbo of possibilities. You are firmly anchored in a reality that has already made up its mind through trillions of tiny, silent interactions. The cat in the box is a lesson in humility, a reminder that we must be careful how we translate math into mental pictures. The quantum world is subtle and strange, but it is not nonsensical. It respects the scale of things. Schrödinger chose a cat because it felt absurd, and he wanted that absurdity to be the takeaway. He wanted us to understand that the rules of the atom are a special kind of logic reserved for the very small and the very isolated. Once we step back into the world of breath, warmth, and solid things, the both-and fades away and the either-or returns. There is comfort in this transition. It means that while the foundations of the world are fluid and open, the structures we live in are sturdy and reliable. The cat is safe because the world is noisy. The mystery of the quantum does not break the common sense of our lives. It merely sits quietly beneath it, providing a foundation that we do not have to monitor to keep it standing. Tonight, let the paradoxes rest. The box is open, the world is definite, and you are exactly where you are supposed to be, held by a universe that doesn't need you to watch to know its own heart. In the everyday world, barriers are decisive and unyielding. A wall blocks a path with absolute authority. A locked door stops movement entirely. If an object lacks the energy to climb over an obstacle or the force to break through it, it stays exactly where it is. This intuition is so reliable that it rarely feels like an assumption at all. It feels like a fundamental rule of existence. We trust that a ball thrown against a brick wall will bounce back every single time, and we trust that the floor beneath our feet will never suddenly allow us to slip through its solid surface. But at the quantum scale, that rule becomes significantly more flexible. Quantum tunneling is the name given to a behavior that seems to defy common sense at first glance. Particles appear on the far side of barriers they do not have enough energy to cross. They slip through regions that classical physics would label strictly forbidden, not by smashing through and not by going around, but by quietly appearing where they should not be able to reach. This is not a magic trick and it is not rare. It is a direct consequence of how quantum systems are described. To understand tunneling, it helps to return once more to the concept of probability clouds rather than solid objects. In classical physics, a particle is imagined as a point with a definite energy. If it approaches a barrier that requires more energy than it possesses, like a car trying to coast over a hill that is too steep, the story ends. The particle reaches its limit, stops, and turns back. There is nowhere else to go. In quantum physics, however, the description is entirely different. A particle is represented by a wave function which is a spread of possibilities rather than a single, lonely location. That spread does not stop abruptly at sharp boundaries. It tapers, it fades, and it leaks. When a quantum particle approaches a barrier, its probability cloud does not pile up neatly on one side and vanish on the other. Instead, the cloud extends slightly into the barrier itself. The likelihood of finding the particle there drops rapidly as it moves deeper into the obstacle, but it does not fall to zero immediately. If the barrier is thin enough, that faint tail of the probability cloud reaches all the way through to the other side. This is the essence of tunneling. The particle does not climb over the barrier, and it does not punch a hole through it like a bullet. Instead, because its existence is wave-like, there is a small but real chance that it will be detected on the far side. The particle does not travel through the forbidden zone in the way we usually think of movement. It simply has a presence there. When probability allows, the event occurs. In the quantum world, the word forbidden does not mean impossible, it simply means extremely unlikely. This distinction is subtle but powerful. Classical rules draw hard black and white lines between what can and cannot happen. Quantum rules draw gradients. There are regions of diminishing likelihood, and while the center of the particle's presence might be on one side of a wall, its edges are exploring the space beyond. Most of the time, the particle behaves exactly as classical intuition expects and bounces back. But occasionally, it does something that feels impossible only because our intuition is tuned to a larger scale. A helpful way to picture this is to imagine a hill in a thick, heavy fog. In clear air, it is obvious whether a person has enough energy to climb to the very top. In the fog, however, that certainty softens. There is a region near the top where a person's presence becomes unlikely but not sharply forbidden. A wanderer might appear briefly where they should not be able to reach, simply because the boundary of where they are is no longer precise. Quantum barriers behave more like these foggy hills than solid walls. This leaking of probability is not a philosophical curiosity or a laboratory quirk. It plays a central role in some of the most important processes in the nature of our universe. Radioactive decay, for example, relies entirely on tunneling. Certain atomic nuclei are stable only because the particles inside them are confined by immense energy barriers. Classically, those particles do not have enough energy to escape the nucleus, and yet, over time, some do. They tunnel, causing the atom to decay. The timing of these events cannot be predicted for any single nucleus, but the probability can be calculated with extraordinary accuracy. This is why radioactive half-lives are so reliable across the span of billions of years. The barrier is real and the escape is rare, but rare is not the same as never. Tunneling also plays a crucial role at the heart of the stars. In the core of a star like our Sun, atomic nuclei are packed together under immense pressure and heat. For fusion to occur and light to be born, positively charged nuclei must come close enough for the strong nuclear force to bind them together. Classically, their electrical repulsion should keep them apart like two magnets pushed together. The energy required to overcome that repulsion is far higher than the thermal energy available, even in the heart of the Sun. And yet fusion happens. It happens because quantum tunneling allows nuclei to slip through the barrier of electrical repulsion. Most attempts fail, but in the vast numbers of nuclei and the enormous stretches of time, even rare events become common. Without tunneling, the Sun would never have ignited, and the universe would be a dark, cold place. Closer to home, tunneling also underlies the technologies that make our modern world possible. Devices that rely on the precise control of electrons, such as the flash memory in your phone or certain types of high-powered microscopes, take advantage of the fact that electrons can tunnel through barriers that classical physics would deem impenetrable. We have built our digital age on the back of this impossible leakage. The key to all this is letting go of the idea that particles are tiny balls. They are patterns of possibility. Barriers do not shut those patterns off, they reshape them. It is important to note what tunneling does not imply to avoid drifting into fantasy. It does not allow particles to teleport freely over vast distances. It does not let energy appear from nowhere. The probabilities involved decrease at an incredible rate as barriers grow thicker or taller for large objects like a human being and everyday obstacles like a wooden door. The chance of tunneling is so vanishingly small that it might as well be zero. This is why people do not fall through floors and why walls do not quietly let objects pass in our daily experience. The rules of the quantum world scale with size. What is possible and even frequent for an electron is effectively impossible for a cat or a person. Quantum tunneling does not break the laws of causality or the conservation of energy. It respects the same underlying laws. It simply applies them through the lens of probability rather than the lens of absolute certainty. In a quantum world, asking whether something can happen is often the wrong question. The more meaningful question is how likely it is to occur. When a barrier is described as forbidden, it means that the probability of passage is suppressed, not that it is absolutely excluded from the realm of the real. This gentle loosening of boundaries is one of the reasons the quantum world feels so different from our own. It trades rigid binary rules for smooth, continuous transitions. It allows nature to explore the edges of things rather than forcing it to stop abruptly at them. And in doing so, it makes room for the processes that enable life to exist. Stars shine, atoms decay, and electrons flow through circuits, all because probability is allowed to leak where classical certainty would draw a firm line. As you drift towards sleep tonight, consider the peace in this softening of walls. The universe is not a collection of cages, it is a place where boundaries are respected but not absolute. The atoms of your body are held together by these same rules, a quiet and persistent leakage of energy that keeps the balance of your being. You can let the walls of your own worries become a bit more porous tonight. Let the rigid barriers of the day fade into the background. The universe is more fluid than it appears, and as the probability clouds of your existence drift in the dark, they are part of a reality that knows how to find its way through even the toughest obstacles. Empty space feels simple and intuitive. Step outside on a quiet night, look up at the dark between the stars, and it appears almost self-explanatory. It seems to be a state of nothingness, an absence of matter, motion, and even thought. For most of human history, this intuition went largely unchallenged by the greatest thinkers. Space was treated as a passive backdrop, a silent stage on which physical events unfolded, but never something that took part in those events itself. It was the container, not the content. However, quantum physics offers a radically different picture, not loudly or dramatically, but with quiet and persistent insistence. At very small scales, the idea of a perfectly empty vacuum begins to lose its meaning. What looks like nothingness turns out to have structure, energy, and activity woven into it, not in the form of obvious motion, but as a kind of perpetual restlessness that never quite disappears. This shift begins with a deceptively simple question. What is the lowest possible energy a system can have? In classical thinking, the answer is zero. If you remove all energy, eliminate all motion, and strip away all heat, what remains is complete stillness. You would have a pendulum at rest, a particle sitting quietly in place, and a universe drained of all activity. There is nothing left to give and nothing to move. But quantum systems do not allow this outcome. Because of the uncertainty built into the very heart of nature, certain properties cannot both be pinned down perfectly at the same time. If a system were brought to a state of complete and total rest, its position and its motion would both be known with absolute precision, and that combination is strictly forbidden by the rules governing quantum behavior. As a result, even in the calmest state available to the universe, a small amount of motion remains. This residual motion is known as zero-point energy. It is not excess energy that can be extracted or harvested for our own uses. It is not a hidden fuel waiting to be tapped. It is simply the minimum background activity required by the structure of quantum physics itself, a gentle, unavoidable jitter that persists even when every effort has been made to remove motion and heat. When this idea is extended beyond individual particles to space itself, the implications become truly striking. In quantum theory, space is not an empty container, it is filled with fields. There is an electron field, a Higgs field, and an electromagnetic field, all saturating the void. These fields cannot be perfectly still. Even in their lowest energy states, they fluctuate slightly, like the surface of a vast ocean that is never perfectly flat, even when there is no wind. They rise and fall, stretch and relax in patterns that never fully settle into silence. This background state is called the quantum vacuum. Though the word vacuum can be misleading, as it suggests an emptiness, what is really being described is the calmest possible configuration of all the fields that exist. It is not nothing, but rather the quietest something that nature allows. Within this calm, fluctuations occur continuously, creating what physicists call the restless void. These fluctuations are often described using the language of virtual particles. It is tempting to imagine tiny particles popping in and out of existence like sparks, briefly appearing before vanishing again into the dark. That picture is vivid and helpful, but it should not be taken too literally. Virtual particles are not objects in the everyday sense. They are better understood as temporary disturbances in fields, features of mathematics that influence how interactions unfold without ever becoming directly observable on their own. They are the accounting tools that reflect the restless nature of the vacuum, rather than physical things waiting to be seen. Still, their impact is very real. One of the clearest demonstrations of this activity comes from what is called the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, classical physics says nothing should happen. There is no electrical attraction and no magnetic pull. Yet, a small force appears, drawing the plates together. This happens because the quantum vacuum between the plates is restricted. Only certain fluctuations can fit in the narrow gap, while all fluctuations are possible outside. This imbalance produces a pressure difference that gently pushes the plates inward. The vacuum itself is doing the work. This effect has been repeatedly measured and precisely matches theoretical predictions. It is not a curiosity or a loophole. It is a direct consequence of the fact that empty space in quantum physics has behavior of its own. The vacuum also influences the properties of every particle that exists. An electron, for example, is never truly isolated. It interacts constantly with the surrounding fields, including those that make up the vacuum itself. These interactions slightly adjust its measurable properties, such as its energy and its magnetic behavior. The corrections are small, but they are precise, and experiments confirm them to extraordinary accuracy. The background activity of the universe matters. It is important to clear away a common misconception here. The quantum vacuum is not a reservoir of free energy waiting to be exploited. Its fluctuations cannot be tapped without cost, and they obey strict conservation rules. There is no hidden power source buried in empty space. What the vacuum provides is not fuel, but structure. It sets the baseline against which all other energies are measured. Without this restless void, the predictions of quantum theory would not match the world that we observe. This reframing of emptiness explains why the vacuum feels so unintuitive to us. In our everyday experience, emptiness means absence. Remove the air from a container, and what remains feels like nothing at all. But at quantum scales, removing particles is not enough. The fields remain, and with them, their unavoidable fluctuations. Even at absolute zero temperature, when all thermal motion has been stripped away, this background activity persists. The universe refuses to sit perfectly still. There is something quietly humbling in that. Even when asked to do nothing, the universe does the smallest amount of something instead. This restlessness is not noise or chaos. It is the fundamental structure of reality. It is the hum of the machine when it is idling. This constant activity has far-reaching consequences. It influences the behavior of every atom, contributes to the stability of matter, and played a massive role in the evolution of the early universe. It also challenges the sharp boundary between something and nothing, suggesting that those categories less absolute than our intuition assumes. Empty space in the quantum picture is not a blank canvas. It is an active baseline, a reference state with rules and behaviors of its own. Fluctuations are not intrusions into nothingness, they are what nothingness looks like when it is governed by quantum law. The restless void does not announce itself with a roar. It hums quietly beneath everything, shaping interactions and setting limits without ever demanding our attention. As you drift closer to sleep tonight, consider the profound quiet of this hum. The room around you is not empty, it is saturated with these gentle, rhythmic fluctuations of the fields that hold the universe together. Even in the dark, even in the silence, the universe is active and alive at its most fundamental level. There is a strange comfort in this. You are never truly alone in a void, for the void itself is a participant in the story of existence. The jitter of the vacuum is a reminder that motion is more fundamental than stillness, and that potential is more fundamental than absence. The fields are there, stretching across the room and through your body, never perfectly still, always holding the possibility of the next interaction. Let the restless void be your companion tonight. It is the quietest something, the gentle pulse of a universe that never stops, even when it rests. You can let go of the day, knowing that the very space around you is a living part of a reality that is far richer and more active than we ever dared to imagine. The night is deep, the void is restless, and you are held in the quiet, steady hum of a world that is always, in some small way, awake. Once fields are accepted as the deeper layer beneath, particles, the question naturally shifts from what things are made of to how many kinds of excitations exist and how they behave. Over the past century, physicists have assembled a remarkably successful catalogue of these excitations, a framework known as the Standard Model. It is not a theory of everything, and it does not claim to be a final, complete explanation of existence, but within its limits, it works with extraordinary precision. The Standard Model is best thought of as an inventory, a carefully organized list of the known fundamental particles and the rules that govern how they interact. It does not explain why these particular particles exist or why they have the specific properties they do. It simply describes them accurately enough that experiments and predictions line up to an almost unsettling degree. It is the ledger of the invisible, the map of the fundamental building blocks that hold our world together. At the heart of this inventory are two broad families of matter particles known as quarks and leptons. These are not objects in the everyday sense, but stable patterns of excitation in their respective fields. They do not break down into smaller pieces, at least as far as current experiments can tell. When matter is analyzed at the deepest level available, these are the pieces that remain. Quarks are the constituents of protons and neutrons, and, therefore, of every atomic nucleus in the universe. They never appear in isolation, they are permanently bound together by a powerful interaction that becomes stronger the more one tries to pull them apart. This behavior is so counterintuitive that it took decades to accept. Instead of weakening with distance, the force between quarks intensifies, ensuring they remain confined inside larger structures. There are several types of quarks differing in mass and other properties, but they all follow the same basic rule. They combine in specific ways to form composite particles, and those composites make up the familiar matter found in the stars, the Earth, and ourselves. Every proton in every atom owes its existence to this quiet but relentless rule of confinement. Leptons form the second family of matter. The most familiar member of this group is the electron, the particle responsible for electricity, chemistry, and much of what makes matter behave the way it does in our daily lives. Unlike quarks, leptons can exist alone. They do not experience the same confining force, which is why electrons can move freely through materials and form currents. Alongside the electron are heavier relatives that behave similarly but decay quickly into lighter forms. These heavier leptons rarely play a role in everyday matter, but they appear in high-energy experiments and cosmic processes, reminding physicists that the particle list is richer than our daily experience suggests. Then there are the neutrinos, members of the lepton family that are famously elusive. They interact so weakly with other matter that vast numbers pass through the entire Earth every second without leaving a trace. For a long time they were assumed to have no mass at all. It later became clear that they do have mass, just extremely little, a discovery that quietly signaled one of the ways the Standard Model might be incomplete. Matter particles alone are not enough to describe the universe. Interactions require mediators, and the Standard Model also includes them. They are often called force carriers, though once again it is more accurate to think of them as excitations of fields that enable interactions to occur. The electromagnetic interaction is carried by photons, excitations of the electromagnetic field. They are responsible for light, radio waves, and the forces binding atoms together. Their behavior is so familiar that it is easy to forget how deeply they shape reality. Without them, chemistry would vanish, and matter would lose its internal structure. The strong interaction which binds quarks together is carried by particles called gluons, which operate only at extremely short ranges. Their effects are confined to the interior of atomic nuclei, but within that tiny domain, they dominate completely. Without this interaction, protons and neutrons would not hold together, and atoms would fall apart before they ever formed. The weak interaction governs certain kinds of decay and transformation. It allows particles to change identity, enabling the nuclear processes that power the sun and drive radioactive decay. Its effects are subtle in daily life, but without it, the universe would be a very different place. Together, these interactions form a tightly woven system. The mathematics describing them has been tested repeatedly and refined with increasing precision. Experiments have confirmed predictions to many decimal places. In terms of accuracy, the Standard Model is one of the most successful frameworks ever constructed by human thought. And yet, it is clearly unfinished. One major piece of reality is missing from the inventory entirely. Gravity does not fit comfortably into the Standard Model. While gravity governs the motion of planets and the structure of galaxies, it is extraordinarily weak at the particle level. Attempts to describe gravity in the same quantum language as the other forces have not yet produced a complete and consistent picture. There are other gaps as well. The Standard Model does not explain dark matter, the unseen mass that shapes the motion of galaxies. It does not account for dark energy, the influence driving the accelerating expansion of the universe. It does not explain why particles have the masses they do, only how those masses behave once they are assigned. Even within its own structure, the model contains numbers that must be measured and put in by hand rather than being predicted from deeper principles. This has led to a recurring sense that the model, for all its success, is more like a highly detailed map than a final explanation. It is a very good map, one that tells us exactly where things are and how they connect, but it does not tell us why the landscape has this particular shape. There is a gentle humor to be found in this situation. The Standard Model is often described as a triumph of modern science, and it is, but it is also a reminder that even our most accurate theories can feel slightly provisional. It is like a beautifully furnished house with a few locked rooms and an unfinished extension. It works perfectly well for our daily scientific life, while quietly hinting that there is a larger story yet to be uncovered. Physicists are comfortable with this state of affairs. The model does not pretend to answer every question. It earns its place by matching reality where it applies, not by claiming total completeness. Its limitations are not hidden. They are studied as the clues to the next great discovery. In practice, this balance has been incredibly productive. By knowing exactly where the model succeeds and where it begins to strain, physicists can design experiments that probe the very boundaries of the known. Every confirmed prediction reinforces our confidence in the inventory we have built, and every small discrepancy offers a vital clue about the next layer of truth. The known pieces of the universe, as described by the Standard Model, fit together with a precision that is nothing short of miraculous. Quarks form the nuclei at the heart of the world, electrons shape the chemistry of life, and force carriers mediate the constant conversation of energy. It is an elegant and sturdy structure. What the model ultimately teaches us is a kind of intellectual patience. It tells us that our understanding can be deep and yet still be incomplete. A theory can be extraordinarily accurate and still be a stepping stone. As you drift towards sleep tonight, let the order of this inventory bring you peace. The universe is not a chaotic jumble of random pieces. It is built on a specific and reliable list of ingredients. Even if we do not yet know why these ingredients were chosen, we can see the beautiful complexity they enable. Your body, your bed, and the air in the room are all held together by the same quarks, leptons, and force carriers. They are working in silent harmony, following the precise rules of the Standard Model to ensure the world remains stable while you rest. The inventory is complete for now, the ledger is balanced, and the invisible pieces of the world are exactly where they need to be. The mystery of what lies beyond the map is a question for another day. Tonight, there is only the quiet, reliable structure of the known, holding the dark in check and allowing the world to proceed with a steady and predictable rhythm. One response to the deep unease surrounding the act of measurement and the mysterious role of the observer is to remove the problem of choice altogether. Instead of asking why one specific outcome appears and all the other possibilities vanish into nothingness, this approach asks a radically different and simpler question. What if none of the outcomes ever vanish at all? This idea forms the foundation of what is known as the many worlds interpretation of quantum mechanics. At first hearing, the name alone can pull the imagination toward the realms of science fiction, endless universes, dramatic splits, and copies of reality branching at every decision. These images are vivid and exciting, but they are not the best way to understand what the interpretation is actually proposing to our logic. At its core, the many worlds interpretation is surprisingly conservative and mathematically lean. It does not add new, exotic rules to quantum mechanics, and it does not introduce special, magical moments of collapse. It takes the existing mathematics exactly as it stands and follows it to its logical conclusion, even when that conclusion feels profoundly uncomfortable to our human intuition. The key takeaway in this mindset is simple. The wave function never actually collapses. According to the fundamental equations of quantum mechanics, the WAV, E function evolves smoothly and deterministically over time. There is no term in mathematics that explicitly describes a snap or a collapse where multiple possibilities become one. Early physicists introduced that idea later as a way of connecting the abstract probabilities of the math to the definite outcomes we see in our laboratories. The many worlds interpretation asks what happens if we simply remove that extra, manually inserted step. If the wave function always evolves according to the same rules, then every possible outcome allowed by mathematics must continue to exist. When a measurement occurs, the system does not choose one result. Instead, the combined system of the observer, the measuring apparatus, and the surrounding environment becomes entangled in such a way that the different outcomes no longer interfere with one another. The result of this entanglement is what we perceive as branching. Each branch contains a consistent version of events, with a single, definite outcome recorded. Within any given branch, the world appears perfectly ordinary and reliable. Measurements have single results, instruments show clear readings, and the logic of our lives remains intact. Nothing feels fuzzy or unresolved to the version of us living in that branch. What has changed is not the experience within a branch, but the structure of the overall description of reality. Branching is not something added by hand to the theory. It emerges naturally from the mathematics of decoherence. When systems interact and entangle, and once different outcomes become correlated with different states of the environment, they effectively decouple. They stop influencing one another. From that point, each branch evolves independently. There is no moment where reality splits with a flash of light or a sound. There is no cosmic fork in the road announcing itself. Branching is quiet, continuous, and constant, happening whenever interactions distribute quantum information into the environment. This interpretation removes the need for collapse entirely, solving one of the oldest puzzles in physics. There is no sudden, unexplained reduction of possibilities, and there is no special role for the observer's mind. The same rules apply at all times to all systems, from the single atom to the entire universe, without exception. For many physicists, this mathematical simplicity is deeply appealing. However, the cost of this simplicity is conceptual rather than mathematical. Accepting that all outcomes persist requires a willingness to let go of the idea that there is only one unfolding history of the world. Instead, there is a vast, interconnected structure of histories, each internally consistent and each following naturally from the same underlying laws. It is important to be clear about what this does and does not imply, to prevent the mind from drifting into fantasy. The many worlds interpretation does not suggest that new universes are being created from nothing. It does not require extra dimensions or exotic physics beyond what we already use. It describes a single universal wave function that contains many non-interacting branches. These branches are not accessible to one another in any way. Once they separate through the process of decoherence, there is no communication, no influence, and no way to move between them. From any branch, others may not exist at all. This is why the interpretation does not lead to practical contradictions or a sense of chaos in our daily lives. It makes the exact same experimental predictions as other interpretations of quantum mechanics. No test performed so far can distinguish many worlds from approaches that involve a physical collapse. The difference lies entirely in how we understand mathematics. Critics of this view often ask where probability fits into a world where everything happens. If all outcomes occur, what does it mean to say that one result is more likely than another? The answer is found in the weight of the branches. Probability in this context is not about whether an outcome happens, but about how much mathematical weight a given branch carries within the overall wave function. Branches are not all equal. Some carry a greater density of the wave function, corresponding to the outcomes that we observe more frequently in repeated trials. From the perspective of an observer within a branch, the outcomes appear random and follow the laws of chance, but the overall structure remains deterministic. This preserves everything that works about the theory while reframing what probability actually means. Another common worry is that the idea feels extravagant, too many worlds, and too much reality. But extravagance is often a matter of perspective. Adding a special, unexplained collapse rule to the equations to make them fit our intuition can also be seen as an extravagant and unnecessary complication. The many worlds interpretation avoids that by refusing to modify the mathematics at all. It accepts the consequences of the equations instead of trying to fix them. This interpretation also provides a clean and elegant resolution to the measurement problem. There is no need to explain how or when collapse occurs because it never does. There is no special boundary between the quantum world of the small and the classical world of the large. Large systems appear classical to us because their branches rapidly become isolated from one another through constant interaction with the noisy environment. What looks like a final choice is simply a branch that has become irreversible. The unease many people feel toward this picture often comes from trying to imagine it too literally, as if there were a literal duplication of their physical bodies. But mathematics does not require that we imagine countless visible copies of the universe fanning out. What it requires is an acceptance that the full description of reality is simply larger than any single experienced history. From inside one branch, the world feels singular, complete, and solid. Your memory, your identity, and your experience remain perfectly intact and unified. There is no sense of duplication or loss. The interpretation does not deny our experience, it explains why our experience feels the way it does in a universe that allows for every possibility. Many worlds is not an attempt to turn physics into a story, it is an attempt to take the existing theory seriously without adding extra, human-centric rules to make it more comfortable. Whether one finds this compelling or unsettling is a matter of philosophical taste, but it demonstrates something vital about the quantum world. The strangeness is not in the interpretation, it is already present in the equations themselves. As you drift toward sleep tonight, let the idea of these hidden branches be a source of quiet wonder rather than confusion. You do not need to worry about the versions of reality you did not choose or the paths you did not take. In the branch of reality where you exist right now, the world is consistent, the stars are steady, and your life is a single unfolding story. The other branches are silent and unreachable, a mathematical testament to the vastness of the universe's potential. There is a peace in knowing that reality is not a narrow, fragile line that might break if the wrong choice is made. It is a wide, robust, and generous structure that holds every possibility in its heart. The night is a time when the branches grow quiet. As your thoughts settle, you are moving along your own unique path, held by the same laws that govern the furthest reaches of the cosmos. The wave function of your life is evolving smoothly without jumps or collapses, carrying you gently into the morning. Sleep is the moment where we let go of the need for a singular answer and trust in the vast, quiet continuity of the whole. As the journey through these quantum ideas slows to a gentle halt, there is no urgent need to tie every thread into a neat or final conclusion. Quantum physics does not reward our desire for absolute certainty that way. Instead, it offers us something much quieter and perhaps more lasting, a shift in how we perceive the very act of existing. Again and again, the deeper our investigation goes, the less the universe resembles a finished, static object. What appears in its place is a continuous process, a world that unfolds through interaction, probability, and relationship. We have seen that reality resists being pinned down completely, not because it is chaotic or broken, but because it is fundamentally subtle. There is a deep intellectual humility in that realization, the comforting belief that everything can be fully known, precisely predicted, and mechanically explained, gives way to something softer and more resilient. It is not ignorance we have found, but a form of restraint, an understanding that some questions do not have final singular answers, and that this is not a failure of our thinking, but a core feature of the world itself. Quantum physics invites this humility without ever demanding a surrender of our curiosity. It has shown us that precise knowledge and fundamental uncertainty can coexist in the same space. It has demonstrated that prediction does not require absolute certainty, and that our understanding of the cosmos can deepen even while the central mystery remains beautifully intact. Letting go of the need for certainty does not mean letting go of meaning. It means releasing the heavy demand that the universe must behave in ways that feel familiar to our macroscopic habits. It means allowing reality to be stranger, quieter, and more open than our expectations once allowed. There is a profound wonder in that openness. It is not the loud wonder of a spectacle, but the steady, rhythmic kind that comes from recognizing how much care the universe takes in balancing possibility and constraint. Nothing in the quantum realm is entirely free, yet nothing is entirely fixed. Between those two extremes, the structure of our entire world emerges. The most remarkable thing we have uncovered may not be any single quantum phenomenon, but rather the attitude that the theory encourages in us. It fosters a willingness to explore without insisting on immediate closure, a patience with the unanswered questions that linger in the dark, and a respect for what can be known paired with a graceful acceptance of what must remain hidden. Curiosity itself becomes the only quiet constant. Every experiment, every complex calculation, and every careful question we have asked about the nature of reality arises from that same human impulse. We do not seek to conquer the unknown or to strip it of its shadows, but to approach it honestly. We listen closely to what the universe is willing to reveal in the click of a detector or the glow of a screen, and we learn the wisdom of stopping where it chooses to remain silent. There is something deeply restful in that stance. The pressure to have final, perfect answers begins to fade. The need to resolve every paradox and fix every blur softens into a state of acceptance. What remains after the equations are solved is a sense of participation in an ongoing, vast conversation, one that did not begin with any single observer and will not end with one either. Quantum physics does not offer us a place to stand outside of reality, to see it as a whole, finished thing. Instead, it offers us a way to stand within it, attentive, curious, and fully aware of our own limits. And perhaps that is enough, to rest with the unknown, to let the questions remain open like windows to the night, and to feel a quiet gratitude not for the arrival of certainty, but for the ability to wonder at all. We have traced the outlines of mysteries as soft as shadows, not to solve them, but to feel the elegance of their shape. We have looked at the dark matter that holds galaxies in a phantom grip and the dark energy that pulls the stars apart in a silent, expanding dance. We have peered into the black holes, where space turns inward on itself, and time slips through our fingers like sand. We have watched the strange dance of particles that are also waves, and the quiet asymmetry that allows matter to exist so that we might be here to witness it. Beyond it all, we have glimpsed the possibility of other worlds, unreachable and unknowable, yet no longer unthinkable. There is a specific kind of comfort in not knowing, in accepting that the universe does not always explain itself to us right away. In that quiet, we can finally find a place to rest. Perhaps by now your breath has slowed to a steady, natural rhythm. Perhaps your limbs feel a little heavier, anchored by the reliable gravity of a world that is measured into place by its own surroundings. Maybe the sharpest questions of the night have begun to fade into the background, like distant stars disappearing behind a soft, clouded sky. Let them fade. Let your thoughts stretch wide and weightless across the fields of probability. The science will be there for you tomorrow or next week, or during some other gentle night when you feel the urge to look again. Falling asleep does not mean you have missed the end of the story. It means you have finally become a part of it. The S2 is a vital part of the scientific journey, the quiet moments, the stillness, and the curiosity that continues even as we close our eyes and let the analytical mind drift away. It is a kind of dreaming that asks not for answers, but for wonder. The universe is a gentle companion that asks nothing of us. In return for its vastness, it simply unfolds, following its own silent, rhythmic pulse. As you dissolve into the unknown of sleep, you are moving through the same fields and fluctuations that build the stars. You are a localized excitation of a grand and ancient field, a ripple in the ocean of reality that is finding its way back to the calm. The story of the quantum world is not a book that ends, it is a wave that continues. Under the quiet stars and within the restless void, the story proceeds without pause. Every atom in your body continues its silent probabilistic dance, held in a balance that is as precise as it is mysterious. You are safe in the hands of laws that have never failed, in a universe that knows exactly how to hold itself together. I hope you sleep well, cradled by the very possibilities we have explored tonight. May your dreams be soft, filled with the shimmering potential of a world that is always new and always waiting. The dawn will bring its own certainties, but for now, the night belongs to the unknown. Rest in the blur, drift in the waves. The whispering scientist is glad you were here for this exploration, but now, it is time to let the words fall away into the silence. I hope you sleep well and dream softly. Good night.